Okay, it's not going to live stream because live streaming.
Okay. Honor, it is now live streaming.
Okay, thanks, guys. Okay, connect to the internet. Okay, we're a bit delayed, but welcome back. Let me put this over here so that it doesn't annoy me. I think what happened was I was not logged into Zoom with my credentials initially. And then while I was on Zoom, I changed my credentials, but it didn't properly update my credentials, in my opinion. As a result, it made this mess. So dynamic updates of credentials is important, probably. That's, of course, a theory, right, based on what happened. But I think when I logged into Zoom second time, I was logged in with my credentials, and it didn't need to update anything. It allowed me to live stream. So this is, I think, poor software design, let's say. You need to be able to update some credentials everywhere to enable basically proper functioning, right? It was not properly functioning, even though I was who I was. Okay, if you're joining right now and trying to make sense of what we're talking about, live stream didn't start on time because Zoom didn't allow me to live stream because it thought I didn't have credentials to live stream because I changed my permissions after. I changed my credentials after logging into Zoom as someone else to begin with, as my other account, let's say, to begin with. Although anyone can log into Zoom, right, without any account. Although I don't know if we enabled that permission in this particular class, probably not. Okay, let's get started. Better late than never. So we're going to continue our exploration of memory, especially memory scaling issues today. I've already introduced RowHammer, so I'm going to go through some of these things really quickly so that we can get to some really interesting pieces in RowHammer, and then talk about some security and reliability issues. Does that sound good? Okay. Can people see this well in the back? Okay. There's a lot of light here, so, but I don't want to turn them off. Okay. Okay, so this lecture is really divided into 4 parts. The first part is called RowHammer, but most of it is about RowHammer in the end. And remember, these are the 4 directions that we're going to examine. And we have started with secure, reliable, safe architecture. We talked about DRAM retention, scaling issues yesterday. Today is going to be more about RowHammer. And this is annoying. Okay. I think this the video is already there, right? We don't need this. You can already see me. Okay. Okay, basically, this is the fact that you can predictably induce bit flips in DRAM memory. And almost all DRAM chips are vulnerable today, actually. When we tested, it was more than 80%. And as I mentioned, this is the first example of how a simple hardware failure mechanism can create a widespread system security vulnerability. And I will also mention that I'm repeating this so that you can get, let's say, your cache is being warmed up right now because we covered a lot of this. But I think it's always good to find such hardware vulnerabilities. I think it's good to search for these actively, in my opinion, because that enables some different way of thinking about hardware going into the future. Because many people think hardware is infallible, right? It's something that should work, that works, and that just works. They don't think about issues in hardware. But going forward, we're going to have a lot more issues in hardware as we keep relying on hardware more and more into the future in our accelerators, etc. Many systems are going to be hardware, let's say, error-prone going into the future, much more so than before because we're going to rely on them more. But I think this is an example of the mindset that, okay, what are we doing wrong in hardware that could affect systems? Remember, we talked about memory performance attacks also, right? That was another example of that mindset. What's happening in hardware that could potentially go wrong that could affect systems? And I like that mindset, as I mentioned at that time also, because that's a vulnerability-driven mindset, and that hopefully enables us to design better systems going into the future that we can depend on. Okay, I didn't show this picture before, but I like motivating some of the issues in systems with references to psychology also. And this is a famous American psychologist, Abraham Maslow. This person had a lot of influence in psychology in the 20th century. And essentially, he dedicated his life to understanding why humans do the things they do. You can see from the titles of his papers, right? The theory of motivation, right? And he came up with something that is probably more famous than his face. And that's this Maslow's hierarchy of needs, that triangle over here. And the bottom is more important or needs to be satisfied before you can reach the top, basically. That's the idea over here. And this had a lot of influence in many fields in explaining, for example, economic decisions, etc., political decisions, etc. We're not going to get into, but you can imagine how this may affect political and economic decisions, right? And what else, right? So basically, he says that your basic needs need to be satisfied before you can go into psychological needs, before you can think about, or most abstract forms of art, let's say, right? That's self-actualization from his perspective. And basic needs, you can see that some examples of it. So I'm going to put reliability and security, only to deconstruct it later. So you need to really start with reliability and security. Like if my phone is not working because of a reliability problem, I don't really care about its energy efficiency, right? That's a simple example. You could argue the other way around, perhaps, in some other conditions. But I like this example currently because my phone is not working very well. Okay, I think I'm giving examples of this bridge, but a bit flip can destroy the safety, security, and reliability of a bridge. And this could be fatal, essentially, right? Somebody on that bridge at that point in time may not survive. In this case, there was no fatality on this bridge, I think, but some other bridge accidents are not good. Bridges are critical infrastructure, and I think computing should be viewed as critical infrastructure going into the future because we're going to use it everywhere. If you don't use it everywhere, okay, maybe it's not critical infrastructure, but if we're going to rely self-driving cars on it, maybe it should be, right? So I think security is really about preventing unforeseen consequences. Again, these people are on a rod. If you get a bit flip on this rod, they may not be very happy soon, right? And again, I think this is a very general definition of security, maybe an unachievable definition of security, but this is the goal we should set. Because if you set a high bar, you can get close to it potentially, right? If your bar is low, you're not going to exceed it probably. You'll be happy when you reach it, but you may not be secure at that point. But if you define security this way, as preventing unforeseen consequences, then you may do things that may get you closer to that bar and much better than the lower bar you may set. And this is true for everything, I think, in general. If you set a high bar, you may get there. If you set a low bar, who wants to get there, right? You can get there, but that may not be interesting for anyone. Okay, we may talk about this more, but unforeseen consequences, of course, is a very general definition, right? So basically, whatever you do needs to be able to adapt, in my opinion, if you want to prevent unforeseen consequences. If you make some decision, if it leads to a security hole, you should be able to change that decision once you figure out that security hole, right? That could be one way. You may not be able to prevent it in the first time, but maybe in the second time, you may be able to prevent it. Okay, so we're going to talk about the RowHammer perspective in the DRAM scaling problem. And I'm not going to talk about this in detail because we covered this in the last lectures. Remember, the problem was DRAM circuit is scaling and it's becoming less reliable as it scales to smaller technology nodes. And any circuit will have this sort of problem, basically. It's fundamental. It doesn't matter if it's DRAM or SRAM or RRAM or flash memory, which we will see in some later lectures. As you reduce the size of the circuit, elements will become smaller, elements will be closer to each other. As a result, they will be more vulnerable to noise based on what's going on, just like we discussed in the retention time last week, right? The cell charge dependent on the charge stored in other cells, as well as what happens in the word line and the bit line, right? There's electrical interference, basically. And I've shown you this picture. So there's clear data from the field also that suggests memory is becoming less reliable. And I think whenever you do reliability studies, it's always good to do both this sort of large-scale studies. You examine many computing systems out in the world, and you check what's going on, basically. You don't have much control. You can instrument and figure out this sort of data, for example. You can look at the errors and analyze them, but you don't have much control because you don't want to disrupt the operation of the system, right? But this leads to some understanding. It's also good to do understand the system in a smaller scale, right? Meaning using this sort of infrastructures where you can actually go and test individual DRAM chips, not during operation, but you're really trying to understand the fundamental issues in DRAM chips. So these sort of studies, they're both good to do. Of course, once you build an infrastructure like this becomes easier to do because normally it's harder to get access to these large-scale computing systems. Certainly Facebook-scale computing systems are much harder to get access to. I mean, you can get access to maybe a cluster that you're running on your own, but that may not be as interesting, right? Because you don't have the large numbers that you have with Facebook's data centers. But basically, there's clear evidence in the field from both large-scale systems and small-scale testing that memory reliability is reducing, right? And we've discussed some of these issues And we've discussed some of these infrastructures. Again, I'm not going to go into the details of it a lot. And we talk about data retention in memory, just to jog your memory again. People remember RAIDER, right? Basically adapting to heterogeneous refresh rates. People hopefully remember balloon filters. That's where we left off last time. Okay, and we discussed that the retention time profiles are dependent on the location of the cell, value of the cell, and the cells around it. That's why that's called a value pattern, right? And it's dependent on time, meaning a random process in this case with a variable retention time. And that's what makes it difficult to exploit, but there's been a lot of work to exploit it. And this is, again, to jog your memory as to what we have covered and what we have mentioned in the last lectures. So we may actually have some guest lectures from my students, Minesh, who just recently defended his thesis, for example, talking about some of the cutting edge work in this area that he's going to present at Micro next week. But stay tuned for that in the future. Okay, now let's jump into RowHammer, because RowHammer is another example, basically. So if you think about the grand scheme of things, I don't think RowHammer is that surprising. Some reliability issues are happening, and this is just a read disturbance related reliability issue, right? But of course, the impact is very high because you show because it's clear that it exists in existing DRAM chips, and somebody can exploit it, right? If nobody can exploit it, maybe it's not as interesting, right? And I will give you the security perspective also later in this lecture, because people actually knew that bit flips are problems, right? People actually did experiments and they tried to induce bit flips. They did induce bit flips, and they basically showed that you can actually attack a system, take over a virtual machine if you have bit flips. So this is actually all known, but it was not interesting to many of the folks in the world because these bit flips required a lot of physical access to induce. You will see that basically you need to heat the machine, for example, or you need to have physical access to a cell phone and, I don't know, cool it down and then do cold boot attacks, which I'm not going to cover over here, but that's something we can cover also as well, maybe in a future lecture, by taking advantage of the retention time. So the idea is, maybe I'll give you the idea basically. Okay, you have physical access to a machine. DRAM, we know that it can retain data for long times, right? Even at room temperatures. You have this physical access, you take DRAM and you cool it down so that you increase the retention times of the cells a lot. And now you inspect what's in memory. If you can do that, that's called a cold boot attack, basically. When the DRAM is cold, you boot the machine and get the data out. Of course, this requires physical access, right? They're not as interesting as something like RowHammer, because RowHammer doesn't require you to have any access other than just executing user-level software on a system. That's why RowHammer has changed the look at hardware quite a bit. Okay, so you know what RowHammer is, so I'm going to go through this relatively quickly. By activating a row many times, you can induce bit flips in adjacent rows. And we're going to actually examine the problem and depth of the problem a little bit more than this. And basically, the initial paper showed that this is a technology scaling problem. And clearly, many DRAM chips are vulnerable in the tested modules. And we discussed why it's happening. Cells are not electrically isolated from each other. And access to one cell affects the value of nearby cells because of this electrical interference in the cells, as well as wires used for accessing the cells. It's very similar to the retention time phenomenon, right? I had a similar slide for data pattern dependence, for example, of the retention time phenomenon. Essentially, it's coupling, cell-to-cell interference. Okay, so for example, I think the intuitive way of thinking about it is when you activate or apply high voltage to a row, an adjacent row gets slightly activated as well, because you don't have perfect isolation in your voltage rails. And as a result, vulnerable cells in that slightly activated row lose a little bit of charge. And if you keep doing this, hammering enough times, activate, pre-charge, a charge in such vulnerable cells gets drained. Okay, this is a good way of thinking about it. Of course, there's an abstraction that we will not go below. There are a lot of device level issues that affect RowHammer in a much more finer way than I explained it over here. So my explanation is very coarse, basically, but how does actually charge flow from one place to another? Those are actually really interesting issues. There's charge tapping mechanisms that go on underneath. And if you're really interested, I recommend looking into the device level literature on RowHammer that we reference in many of the papers. And also there's a Safari seminar that we did actually with Andrew Walker at the beginning of, summer, where we talked about some of these device level issues. You can also read that. But that's, I think, beyond the abstraction level of this course, let's say. I don't want to go into the device level. I don't know, maybe it's interesting. How many people are interested in device level issues? Okay, there are quite a few. And so I would recommend you look at some of those papers. if you read our retrospective paper in 2019, you will see a lot of references to those device level papers that theorize basically why RowHammer is happening. There are multiple effects that people theorize. They try to also experiment and show to prove the effect that they're examining is actually dominant, or at least has an effect. But I'm not going to go into it right now. Maybe we should put some of those papers as potential extra credit readings. Can you handle that, Rakesh? Okay, that'd be good. That way you can read it and also get extra credit, right? Okay, I'm not suggesting everything you read should be extra credit, but I think it's not bad. Okay, clearly there are higher level implications as we discussed. And I think this is a slide that I did not show. Did you remember seeing the slide? Probably not, right? So basically this is a higher level implication. This is the program that we wrote when we actually released the RowHammer paper. We released the code on GitHub also, you can find it. And basically it's an x86 program. What it does is, essentially, it bypasses the caches by flushing the cache lines that these instructions are accessing. It basically tries to access 2 cache blocks repeatedly, and ensuring that these are never cached in the processor caches, right? And what does this mean? This means that you keep accessing the DRAM row for X as well as Y, and you do it in an interleaved manner, right? So what this program does is it avoids caches, as I said, by flushing. It avoids row hits by reading Y in another row in the same bank, right? So that's how you bypass the row buffer. There's a single row buffer. You don't want things to be serviced from a row buffer if you want to do a hammer on the activations, basically. Okay, so basically this user level program can cause RowHammer. Of course, you need to select address X and Y carefully such that they map to the same bank, right, in DRAM, as we discussed. Okay, so if your chip is vulnerable, hopefully this access pattern causes RowHammer. If your chip is vulnerable, this access pattern may not cause RowHammer. Why? Because this may not be the best access pattern, right? Meaning you may have selected X and Y, they're far away from each other in the bank. And individually, yes, you're activating them, but individually the number of activations you do are not enough, right? Or maybe the rows that you picked are not really that vulnerable. So later, what folks from Google did, well, let me talk about our program first. Basically, this is what we saw. We basically saw that in many real systems, you get bit flips. And we said, basically, anyone can exploit these bit flips. And there are many ways of exploiting, but our purpose was not to show how to exploit these bit flips. So clearly, it's a real reliability and security issue. So going back to this access pattern, access patterns are important. So if you pick X and Y such that you sandwich only one row between them, then you increase the probability of failure, right? Because you're really hammering one row in a double-sided manner, right? It's called double-sided RowHammer, and that's what we mentioned it in the paper, but we didn't really evaluate it. But Google folks did, and they saw even more bit flips. And then, of course, you can say, okay, maybe there's a better way of ordering the instructions in the CPU. If you're doing this from the CPU side like this, not the FPGA. FPGA is direct access, right, to DRAM. But if you're doing it to the CPU side, maybe there are different instructions you can use to hammer. They may have different properties, different ordering properties. In fact, you don't need mfence, for example. You don't need a fence instruction for this, we found out. So you can reduce, you can change this loop. And that's something really interesting I think you may want to look into. I'm going to mention a paper from 2020 that examined these effects. Okay, so basically, I think the key is when you're attacking hardware, you need to know what you're doing in a sense, right? Different orderings may lead to access patterns. In fact, in my opinion, if you go back over here, some of the chips that we tested were not vulnerable, right? Yeah, or we're not they're not vulnerable with the access pattern we tested, basically. But some other access pattern may actually see more, create more bit flips. So always keep that in mind. I find it fascinating because it's an access pattern dependent fault, right? It's not independent of the access pattern. Okay, I think we also discussed this, but basically, the reason this is both reliability as a security problem is it really breaks memory isolation, right? Fundamentally, you should really isolate. Whenever you access memory, you should not have unintended side effects on other locations in memory, or even this location in memory if you're not writing to it, right? Basically, there should be no unintended side effects, but now you're getting unintended side effects. And that side effect can be exploited for malicious purposes, or it can just be a reliability problem, data corruption problem. And we said that it can be exploited, and Google Project Zero folks showed that. And I would recommend actually reading their paper as well as watching their talk. Mark Seaborn has a nice Black Hat presentation about this, and Thomas Dullien who is a famous hacker actually, has many presentations about it. He did a lot of work in software security, Thomas Delian. He's one of the authors of this work by Google. I'm going to mention that in the next slide. But when he started working on RowHammer, or after he started working on RowHammer and actually figuring out how unreliable hardware was, he basically says RowHammer was a big game changer, an eye opener for me, basically. So there's a class of attacks at the software level, and he basically went into the class of attacks that's completely different. And I think of it the same way, actually. Okay, so this is what they wrote, Seaborn and Dolian, in their blog post. They basically learned about the problem from our work, which was published maybe close to a year before, let's say. But of course, they learned about it earlier after it was published. They basically repeated the experiments, and they found out essentially the same thing: a selection of laptops, and some of them are vulnerable to the problem. And they actually built 2 attacks to use this effect. One is basically, one is not that interesting. Basically, it takes over the Google native client. You could think of it as taking over a virtual machine, which we will discuss later on. But the other is very, very interesting. I think as a user level process, you can induce bit flips in page tables such that you can take over the entire system. And again, I'm not going to go through details because I would like you to watch the presentation, read the paper. I actually had slides somewhere, but maybe not in this presentation. But basically, what the process is trying to do is it's trying to induce bit flips in page table entries. So you have a memory location, memory row you're hammering, and the next row belongs to a page table. Page table really has the access protections for a particular page, right? Now, if you can somehow magically hammer a page table entry that belongs to your process, which is you're the malicious attacker user level process currently, but you hammer this page table entry that belongs to you, meaning that affects your permissions to some locations. And initially you don't have permissions, just read permissions, but you flip the right bits such that you gain write permissions. Then you escalate your privilege, right? You increase your privilege. Now, this may not be that interesting if what you gain permissions, write permissions for is just some data, right? Now, the creativity of this attack is that they're able to bit flip page table entries that essentially provide access to the process's own page table. Meaning this page table entry determines your permissions to write to your own page table. Does that make sense? Normally, you should not be able to write to your own page table. That's the privilege of the kernel, right? But they flip the bits in such a way that the process can write to its own page table. And once you can write to your own page table, then everything is gone. All of the permissions in the system belonging to that user level process are actually kernel level at that point. Because if you know what you're doing, you know the structure of the page table. It's written in the architectural documents. You can figure out the structure also in different ways, of course. And basically, you can now change the permissions you have to any part in the location in the memory. You can basically change the translations you have, for example, such that you can gain write access to some kernel module, right? Because you're changing your page table. Does that make sense? So that's what's fascinating about these attacks, I think. And these folks are the first ones to actually take advantage of this RowHammer bit flip and turn a user level program to gain kernel level privilege, essentially. Again, I gave you the high level idea. Of course, making this work is really, as we discussed last time, right? Ideas are dime a dozen, but making it work is really a contribution, and the way they make it work is interesting. And later, there are many attacks that make it work in different ways. But these folks are the first one to make it work. Maybe not in the most methodical way, but they made it work, basically. And they showed this proof of concept. Okay, I don't have the slides, but please take a look if you're interested. Any questions about this? Okay, cool. Okay, so I mean, we've discussed the RowHammer vulnerability, and I like analogies, and this is from another hacker, another very famous hacker. These hackers go by some names. They don't use their real names. They use some other name, basically. I think this hacker was Motherboard Weiss, something like that. I don't remember exactly. Don't quote me on it exactly, but basically, this person has some good insight. It's like breaking into an apartment by repeatedly slamming a neighbor's door until the vibrations open the door you were after, right? So if you're stuck in this room, everything is closed, keep banging on the walls and maybe the door will magically open if it's vulnerable to this interference, right? Interference effect. Okay, that's a joke, of course. Okay, so let me give you the history a little bit. So this is a paper that was written in IEEE Security and Privacy in 2003, I think. Clearly way before RowHammer, right? And these folks essentially had a very nice, interesting insight. And the idea was to use the memory errors to attack a virtual machine. Basically, you don't have privilege in a virtual machine when you're running in a virtual machine. Can you escalate your privilege by inducing memory errors and taking control of the virtual machine? It's similar to taking control of a user system, right? It's just levels of privilege is different, right? I think they could have easily taken control of the kernel as well, but that's a slightly more difficult attack. But the fundamental principles are, in a sense, similar. So basically, I don't know which part I would like to read, but yeah, I don't want to read much. I think, but basically, their goal was really to attack smart cards and tamper-resistant computers. Basically, you have physical access to them. That's probably true, to the outside of the computer, and can use various means to induce faults, like temperature, as we will see in a little bit. Heat, basically, they have successfully used heat, and they basically show that by inducing these bit flips and by designing crafting a probabilistic attack, you can avoid the type checking that's done by the virtual machine, and basically you can become the hypervisor, let's say, in this particular case, if you want to use some familiar terminology. And again, I would recommend reading this paper. Did we assign this as a? Yeah, maybe this may be a potential reading. If it's not, please let's add it. Like not as an extra credit, of course, right? not something that you have to do, because I think this is very fun to read. In fact, I read this a long time ago, and probably when it came out in 2003 when I was in graduate school. But of course, I didn't know what to do with it at that time. But basically, you can see that if the attacker has physical access to the outside of the computer, they can induce memory errors. And they look at other different ways. But this is their infrastructure at the time, basically. I don't know if you can see it, but there's a lamp over here, a clip-on gooseneck lamp. Some people may have used it, right, when you're reading papers or something. A 50-watt spotlight bulb and a digital thermometer. And they basically, because of the heat that's generated by this lamp, you get a lot of memory errors. And of course, the creativity is how to take those memory errors and turn them into an attack, right? And that's essentially what they do. And they show this proof of concept nicely. Again, I'm not going to go into the details of it. Please take a look. Does that sound interesting? Yeah. So basically, this shows that the fact that memory errors will lead to attacks was known long before RowHammer. And this is 2003. This paper had interesting impact, not a lot of impact, let's say. Meaning people say, oh, okay, this is interesting, but how realistic is it, right? That's always true with attacks in general, right? Clearly, there may be some cases where this is realistic, right? When you have a smart card reader, for example. But again, the other downside of this is errors are not that repeatable here. You're not really controlling the errors that much. RowHammer, if you think about it, you can actually, if you have time, you can basically figure out which parts of your memory are vulnerable and figure out which bits are exactly vulnerable and force the operating system to allocate things to places that are vulnerable. So if you're basically, you can be very methodical about how you construct the RowHammer attack because you can repeat the errors. So I will show you later data that if a bit is vulnerable due to RowHammer, it's going to be vulnerable again and again and again and again and again. That may not necessarily be true because you don't have a lot of control. This is a very coarse-grained control when you're putting a lamp over memory. Make sense? And clearly, this is not software control, right? Okay, so there's some readings I'm not going to talk about in detail. This is maybe an even older slide, but basically, let me very quickly maybe. Clearly, this is the first paper, and this is our source code. This is Google's source code that builds on our source code that does double-sided RowHammer. Other people had similar ideas that basically you can get rid of cache flush, for example. So attacks can improve. You don't need to flush from the cache using. So basically, some people said, "Oh, you don't have cache flush instructions," or if you don't want these attacks, make the cache flush instruction privileged, such that the user level cannot call the cache flush. Well, what do these people do? well, I don't need cache flush. I can evict cache size in different ways, right? As a program, by causing conflicts in the cache. So that's not a good solution, basically. That's not a principled security solution. That's a hacky solution, let's say. And clearly, it's not a solution. That's how I think you need to be careful about the solutions that you provide to security issues. You cannot just come up with, oh, okay, I'm going to make this non-privileged. In fact, this is actually the mindset that we had from industry. Industry said, oh, okay, your attack requires cache flush. I'm going to make it privileged, and it's useless. So they're not thinking a lot, maybe, right, if you think about it. So I think there needs to be a mindset change in terms of security, like we talked about at some point earlier. I'm going to talk even more to make it much more, let's say, methodical in terms of how we think about these attacks. Okay, other folks also show the same thing, by the way, CL flush free RowHammer, and they also had some mechanisms that I'm not going to talk about. You can read it again. So other folks show that you can actually exploit memory duplication. Again, I'm not going to show this in detail. Clearly, there's a lot of work. If we cover all of them, that could be a lecture course by itself. Yeah. Let me see. I mean, people reverse engineer, for example, mapping of physical address in DRAM, like we talked about last time. Because if you want to know what row is close to what row, and if you really want to place the data or force the kernel to place the data in a particular row, you need to know all those levels of mapping, right? And people have reverse engineered these quite well as early as 2016, as you can see over here. And you basically can read, this is a technique that allows a malicious guest virtual machine to have read and write access to arbitrary physical pages on a shared machine. Basically, your data is not private, or even worse, right? Okay. Let's see. Yeah, I mean, people, of course, once you have this sort of access, you can break public key authentication mechanisms that have been verified in many ways. And this is an interesting one that I'm going to talk about in a little bit, because I think that's very clever also. Basically, these folks, it's called DRAMmer. Okay, another thing that was said during RowHammer, we wrote our paper, right? We showed Intel and AMD systems are vulnerable, clearly. We didn't test everything because we don't have access to everything. But clearly, if you have a good enough memory controller, you can induce these bit flips. Some people said, oh, ARM machines are not good enough to do this. So ARM machines are more secure. That's another very hacky argument to actually improve your security, right? But clearly, ARM machines are not, any memory controller should be good enough to do enough activates within a refresh interval. And ARM machines are no exception. And these folks show that ARM-based Android systems are vulnerable. And also, more importantly, maybe deterministically vulnerable. Meaning, the operating system, the Android operating system, has a very predictable memory allocation behavior. It's an algorithm, and you know what it is. So what you can do is, you can exploit this. By doing memory allocations and deallocations, you can fool the operating, basically, you first figure out a cell phone. You basically, somebody downloads your source code on a cell phone. And this attack program, application, user level, figures out what bits in your memory are vulnerable, figures out a page, a number of pages that are bad for RowHammer, basically vulnerable to RowHammer, and it does the allocation and deallocations carefully, very, very carefully, such that the operating system allocates the program's page table in a location that they know is vulnerable to RowHammer. And if you want to really know exactly how to do it, read the paper. It requires some thinking when you read. It's not easy to access, let's say, as well. But that's the idea, basically. If you know what the operating system is doing is allocation, deallocations, then you can fool the operating system to allocate a target page to a RowHammer vulnerable row, victim row. And then you hammer it, of course, and then you gain access. So they basically show that you could do it deterministically. And that's nice, I think. Okay, let's see. Yeah, I'm not going to go into the details, but you can see a lot of attacks over here. Maybe I'll mention some of the other ones. Actually, I have some pictures of some of them. This is also interesting. These folks show that you could use a GPU to accelerate RowHammer attacks, because GPU is can generate many activations or many memory requests. So you could actually accelerate RowHammer attacks and also compromise browsers on mobile devices. And they basically show under 2 minutes, let's say. That's their result. I don't know, I haven't verified it, but it sounds plausible to me. Okay, these folks show that you could do the attacks remotely in a remote direct memory access engine, etc. And these folks show the same thing essentially, and there are some protection mechanisms, etc. So it's a very brief history that doesn't cover all of the literature, but you can see how much creativity from the security community has been unleashed because of the fact that you could do these bit flips, you could induce these bit flips in real hardware. So I think this also points to something that I will mention because I think it's important. This is unfortunately how the computing stack has been organized, right? Remember the picture transformation, levels of transformation. I had the problem at the top, algorithm and different layers, and then the architecture layer, microarchitecture, logic, circuits, and devices. Security community tends to deal with things that are real. So they basically, if something requires hardware modification, it's mostly ignored, let's say. I think this is an example. So people clearly knew memory errors are a problem, right? But inducing them required a lot of physical access and maybe hardware modification. Basically, they didn't think it was as real. They needed RowHammer to start thinking that, oh, this is really real, right? I mean, in a sense, true, right? RowHammer is real, and you can induce it through software. But I think this also shows you that there's a divide, even in the research community, between software and hardware. If you cannot induce these bit flips in software easily, forget it. It's not a vulnerability from the perspective of even the cutting edge research that's happening in the field, right? If you can induce these bit flips in software easily, okay, now the game is on. Now now we're going to look into this a lot, right? And that's what happened essentially. And I think this is unfortunately, this is how big the gap between software and hardware is today. I think it's good to break that mindset, but it's also good to realize that that's how it is sometimes. Yes. Exactly. I think I would argue so. Yes. I mean, in the paper, even we recognize that read disturb errors are everywhere, right? We talk about other like flash memory, and in fact, we were inspired by the work we were doing on flash memory. I will mention that also later on, where we saw a lot of read disturb errors. So fundamentally, read disturb errors are everywhere, but showing that they're real and they can be they can cause real bit flips in real systems, and analyzing that is important. Okay, any other questions? Okay, let me give you some more stories, basically. So this is actually the first folks who picked up on RowHammer were memory testing folks, as you would expect, right? Because memory testing folks like testing memory, ensuring that you don't have bit flips. And they basically said, what they did was, after they read our paper, they basically designed this hammer test 13. So Memtest 86 is one of the biggest companies that produces this test. So sometimes your machine may run test programs when you boot up, for example, or when you change the RAM, or periodically, you may be able to force your machine to run the Memtest also. Sometimes there should be a way to do that. Actually, you can download the program and run it as well. But basically, this is all systems run this sort of program. They don't have to be exactly Memtest 86, but this is one company, one big company that does it. But basically, they said this hammer test is designed to detect RAM modules that are susceptible to disturbance errors caused by charge leakage, blah, blah, blah. I mean, it's certainly interesting. Their test is not good enough. Actually, we tried it. Because again, this is very access pattern dependent, right? So the way they do the test is by using CPU instructions. If they used our test, then our test has been improved over years, right? So this sort of testing is also a hard problem, by the way. It's good that they include it, but it's hard to really have a good test. But the interesting thing is, okay, they have this test and they later released this, and they started getting a lot of calls from customers saying, oh, we're getting errors in Hammer Test 13 all the time. So what's wrong with my module? And they had to add this to their website, saying the errors detected during test 13, albeit exposed only in extreme memory access cases, are most certainly real errors. So they basically say it's real errors, and yeah, they basically try to justify it. I guess you can take a look at what they're saying. Okay, it may be of greater concern. It's a speculation basically over here, but they had to say that this is real, and we cannot do anything about it basically. I guess there's detection and mitigation. That's also speculative. That's put by this company. We're going to talk about this detection and mitigation because it's become a mess in industry recently with this targeted row refresh algorithm that they mentioned over here also. But this is for your benefit. If you're interested in reading, you can take a look. Maybe the webpage is still the same. I don't know. I haven't gone there very recently. Okay, so we'll talk about mitigations after we talk about security element. I mean, clearly you can breach memory protection. This is slides from our ONISCA paper, basically. We said that you can breach memory protection. Basically, you can corrupt pages belonging to some other program, and someone can hijack your computer. In the paper, we wrote that using these disturbance attacks. But that's not our goal in this work. In fact, it's good that it's not our goal because that would take us a long time to actually create that disturbance attack. And clearly that would be a different work, like other works have proven, right? So I think it's also good to know in research where to say, okay, this is the time I'm going to release the results I have, right? We could have waited and gone into the territory where we don't exactly know how to construct this attack, right? And we didn't do that. Okay, so these are some interesting papers that I mentioned. I think these folks from TU Graz show that you can gain unrestricted access to systems or website visitors by doing these attacks through JavaScript in a server. I mentioned this RowHammer work basically. I'm not going to mention it again, but these are some interesting papers. This is GPU work. This is RDMA, remote direct memory access. You can hammer memory in a remote machine basically. This is interesting. This is more recent. Basically, these folks, even though you may not have gained privileges, you can leak private data from some other program, basically. Again, this is a sophisticated attack. I'm not going. We don't have time to go into the details of all of these attacks. I'd recommend reading the paper or watching their presentations. So, even though there may be protections in place that don't allow you to get kernel privileges, you may still leak some data, basically. And okay, there are some other works over here. And I think I mentioned these works. These are more recent works that where people examined the vulnerability of neural network acceleration mechanisms, hardware, inference mechanisms, basically, and their vulnerability to these RowHammer attacks. And this work in particular, for example, shows that a neural network that's otherwise reasonably accurate, 90%, maybe not enough, of course, right? You always want higher accuracy. Depending on your purpose, 90% may be enough. But if someone targets your neural network and attacks it, your accuracy may be much worse than 90%, basically, 10%. In fact, that's not good, right? Clearly, this sort of issues affect all computing systems because DRAM is used everywhere, right? That's one, I guess that's one downside of DRAM being so popular and having also this vulnerability. Any system is vulnerable right now. And again, I don't know if anyone claimed that our neural network accelerator was not vulnerable to RowHammer, but this work is a proof of concept showing that it may be vulnerable. So you cannot take this lightly in the end. Any bit flip can cause problems. And I think we do need to change the mindset that to the level that I mentioned earlier, right? Security is really about preventing unforeseen consequences. And you cannot try to hide away bit flips, like I think industry has been doing for some time, unfortunately. I think that has to change. Okay, so this may be another security implication once your program, once your computer is having a lot of bit flips, now you become the security threat to your computer, maybe, right? I don't know. I'm just joking, of course. Or maybe that's the solution to the problem. I don't think so. Okay, so let's go into understanding RowHammer a little bit, and then we're going to talk about solutions. Any questions so far? May I give you a bench? Yeah, please. Uh-huh.
Is the feasibility of that like later, where there's like some fundamental
So how feasible is the DRAMmer work, basically? That's what you're asking. Well, I think that's a good question. I don't know. I mean, with these sort of security attacks, it's always a question how feasible it is, right? But if somebody's doing it and if you don't have mechanism to detect it, you also don't know if somebody's doing it right. That's the downside, I think. I think RowHammer lowers the bar for many people to do this sort of attacks. And when people invest a lot, I mean, let's say governments invest a lot to attack maybe other governments, maybe attack their citizens or other citizens, etc., or get access to private data that they should not have access to, etc. Right? So there are actors in place, I think, that are willing to do much more than just a RowHammer attack, let's say, and RowHammer lowers the bar. So in my opinion, if you take that perspective, these attacks may already be happening, and we don't know, right? That's the danger with security, right? You cannot really rule out any attack as not happening, especially at the hardware level. Software level, okay, if you know the attack, you can detect it. At the hardware level, currently we don't have detection mechanisms, right? If you put detection mechanisms, maybe you can figure out, and maybe you can actually prevent these attacks. Does that make sense? So my answer is I don't know. I think it could be practical because these folks showed a good proof of concept. They actually have an app. I don't know if you can still download it, the RowHammer app. Search for it in the Android store, I guess. But again, how often is it successful? How practical it is? Yeah, I don't think there's any data on it.
I guess it makes more sense if you're on some alternate, not break down all of this.
Yeah, maybe. Yes, please. Maybe that system is not working because I couldn't hear. Oh, it's not working?
Normally,
Is there a way to, okay, how about now? Try it. Oh, that's my microphone. Sorry. Okay, go ahead. Maybe I'll try to repeat it.
the original paper said that over 80% of the tests is wonderful. So after that, there's some that are so you believe that it's
Yeah.
that you should have the right
Yeah, so that's a good question. Basically, if you remember that picture, I think some of them are resistant because some of them are older. And RowHammer is not a big problem, like the DDR3 chips, older DDR3 chips we tested that were manufactured in 2010. But I think from the newer ones, it's because we didn't have good access patterns. That's my conjecture, of course, because we didn't test the same chips again. We test other chips. I will show you results from other chips that basically show much more vulnerability in newer chips. Okay, let's try to understand this a little bit. So as I said, we're not going to go into the device level root causes, but there are multiple different things that happen in device level that are interesting. Coupling is interesting. Sometimes conductor bridges get formed between transistors, for example. Again, this is another form of coupling, but it happens in a different way. And sometimes carriers get injected from one place to another. And sometimes permanent damage can happen due to hot carrier injection. But yeah, I think these all have some effects. And you can read the papers, relevant papers that talk about it. And when we wrote the paper, this was confirmed by at least one manufacturer, but right now I think all of them confirm the causes. Okay, so with the testing infrastructure, we did a lot of studies, as I mentioned, and these were the 129 modules we tested. 80% were vulnerable, as I said. You can see victims per module, and basically you can see different results over here. I'm going to show you some example results. I'm not going to show you everything over here. Clearly, that will take some time, right? But some interesting example results. Let's take a look at. And the first one is from the memory controller's perspective. What is the address difference, row address difference between the victim row and the aggressor row? You hammer aggressor, and who gets bit flips basically? What's the distance? Assuming that memory controller's mapping is exactly the same as physical mapping, row address difference should be plus and minus 1, right? 0 is, of course, the victim row and aggressor row being the same, but that shouldn't happen because you're not inducing bit flips on yourself because you're refreshing the row by doing activate and pre-charge, right? Remember the refresh part. And most of the time, that's the case, actually. So this kind of makes us think that from the memory controller's perspective, you have a logical address mapping. And most of the time, that's similar to the physical address mapping, right? And that's the case. But sometimes that's not true. There are some, at least from the memory controller's perspective, some rows are not adjacent. Now, there are multiple reasons for this. This could be there's some internal remapping going on in the chip due to, for example, a row may have hard faults. You remap it somewhere else so that the row can operate, right? Like we discussed last time. internally, DRAM manufacturers did that. That could be one reason. It could be that there's some algorithmic remapping going on from the logical row address to the physical row address. And that's true also partially. Later works explore that basically. There's some algorithmic remapping going on. Some bits are, for example, changed, swizzled, so that the logical address gets mapped to different places in the physical address space. That is done due to reliability reasons, for example, also inside DRAM. So these are the two major reasons, basically. But most of the time, aggressors and victims are adjacent. So you can take advantage of this, basically, if you're an attacker. Right? Most of the time, you're lucky, let's say, because you know what's physically adjacent. But even if that's not the case, people reverse engineer these effects. Yes? Oh, sorry. ABC are 3 different manufacturers. So we didn't release the name of manufacturers for the reasons we discussed last time, right? I think you asked the question, maybe. Or somebody asked the question, I don't remember. It came from this locality. Let's say you asked the question. Okay, thanks. But you were sitting somewhere else, maybe. I don't know. Yeah, okay. Yeah, those are different manufacturers. And these are the worst chips. But this is similar, the pattern. This is from a single chip from each manufacturer, but the pattern is similar for many chips. Okay, so let's move on. The access interval is interesting, meaning basically this is how frequently access the aggressor, activate the aggressor. And DRAM has a limit. Basically, it says you cannot activate a row again unless you wait for 55 nanoseconds. We'll talk about timing parameters in DRAM in a later lecture. You'll see why it's there. But to make sure that you get the right data, basically. Otherwise, the circuits are not stable enough to provide the right data. So clearly, that's not allowed. So we varied it, of course, with an FPGA-based memory controller. You can say, okay, I'm going to activate more frequently or less frequently. And you can see that if you keep activating less and less frequently, at some point you get rid of the bit flips. Why? Because you're not doing enough activates within a refresh interval, and that's the idea. But you need to increase your access interval a lot, like by 5 times at the very least for this worst chip, and by almost 10 times at the very least for this worst chip from the other manufacturer over here. So less frequent access as expected lead to fewer errors. This may also be proposed as a solution, right? Change the DRAM standard such that you don't access DRAM. You're not able to activate frequently, but that's a bad solution because that loses performance significantly, as you can see over here. Okay, refresh interval, probably you can guess also what this curve would look like, but 64 milliseconds was the common standard refresh interval at low temperatures. And clearly we can reduce it or increase it, the interval, yeah. Make the refreshes more frequent or less frequent by going from left to right in the FPGA infrastructure. And the curves look like this, basically. At 64 milliseconds, you get a lot of errors. If you make the refreshes more frequent, at some point, you get rid of all the errors, of course, right, as expected, because you're refreshing very frequently. You don't have enough activates you can pack within a refresh interval before you lose charge. But unfortunately, that refresh interval is bad, meaning you need to refresh 7x more frequently if you want to get rid of all of the errors. And that's not good, right? Clearly. We discussed the issues with refresh in the latest lecture. This clearly you can gain more reliability against RowHammer by refreshing more frequently. And this is the reliability energy trade-off that I mentioned last time. Also a performance trade-off, of course, but you can expend more energy, refresh energy, and waste your performance and get more reliability, but this is not good. Okay. But this is, as we will discuss, this is the solution that was adopted by industry. Of course, they didn't make it 7x frequent because that would be terrible. They increased the refresh rate by about 2x to at least to reduce the vulnerability to RowHammer. So they did actually take action because this was the easiest action that you can take for existing DRAM chips, right? Okay, so this is expected also. More frequent refreshes lead to fewer errors. And probably you would also expect data pattern dependence based on what we talked about, right? Last time, I showed you data pattern depends on retention time. Well, RowHammer is not that different. Meaning, because there are charge-based mechanisms that are in play, coupling-based mechanisms that are in play, the data patterns that you have in DRAM cells, DRAM cells in the victim and aggressor DRAM cells lead to different vulnerabilities. And if you read the paper, you will see that this pattern, row stripe pattern, leads to 10x more errors Why? Because again, coupling is much worse here, right? Here, you don't have as much coupling because capacitors are all similar. Whereas here, you have a lot of coupling between the victim and aggressor rows. Okay, there's a lot more analysis that you can do, of course. I'm just summarizing the analysis, but if you're an attacker, you can use this for your own. And later works actually show that you can use data pattern dependence to build better attacks. Okay. Okay, so there are some other results that are interesting. So we talked about retention, and we talk about retention weak cells, meaning leaky cells, right? There's almost no overlap between cells that are vulnerable to RowHammer and cells that are fundamentally leaky. Now, this may be surprising a little bit because you can say, oh, okay, the cell that's very leaky should lose its charge much earlier if you hammer it, right? And that's, yeah, intuitively that's true, but it turns out these are very different mechanisms in terms of errors, right? Retention errors require fundamental just leakage. You need to have fast leakage through the RC path, whereas RowHammer is completely electromagnetic interference and some other effects, right? So there's basically some overlap, but not a large overlap. Air is not strongly affected by temperature. So we actually have some paper that looks at this more detail. So this is a bit debunked today, let's say, in 2021, after 7 years. So take a look at the paper that's coming up. Maybe we'll have another presentation related to it. Errors are repeatable. This has not been debunked, and this is really bad for security, right? If you can repeat the same error, if you find a bit to be vulnerable, you're going to find again and again and again and again, basically, and you can repeat basically. This makes it easier to attack, basically. Errors don't just happen intermittently on bits. Okay, so there's other results, some other results. There are as many as 4 errors per cache line, meaning simple error correcting codes. Normally they correct 1 error and detect 2 errors. That's what single error correcting, double error detecting SecDet means. Are not good enough to prevent all errors. So ECC doesn't solve the problem. Or if you want to solve the problem, you need to have much stronger ECC error correction codes, which leads to other overheads, right? So this later also was looked at by other research, and people actually, this was actually an interesting discussion also. Basically, we always argue that ECC is not a good solution to this problem. I'm going to mention other reasons also. Basically, ECC error correcting codes, what they do is basically they encode data in some way such that if you get an error, you can recover the original data, right? So of course, to be able to do that, you need some redundant encoding. Meaning if you have 8 bits, let's say you have 3 more extra bits. I'm just making it up, of course. Usually the granularities are higher. Let's say you're encoding 64 bits. You have 64 bits and you have 8 extra bits. And these extra bits encode something about the data. They're called error correcting codes. And if the data changes for some reason, or the error correcting code changes for some reason, because of an error, you can reconstruct the original data. Hamming is famous for this, whose paper you read. Hamming codes are actually the original codes that enabled this. And then later, there was a lot of error correcting theory that was built, of course. But basically, clearly, this is effective for some number of bits. And usually, you design the code such that it can correct some number of bits and it can detect some number of bits, basically, bit errors. And usually, it can correct fewer bit errors than it can detect, because detection is an easier problem, right? Correction requires even more information, redundancy to correct. Okay, so that's ECC, very short introduction to ECC for you. But if you, so when do you want to use something like this? I would argue that ECC, error correcting codes, are extremely useful when you have no idea why the errors are happening. I get a bit flip randomly somewhere. I have absolutely no idea. Then error correcting code is a great thing to use, because it corrects, it basically protects any bit. Right? Okay, now let's take a look at RowHammer. With RowHammer, we have a very good idea why the errors are happening. Right? Clearly, there's a clear access pattern that leads to the error. Does it really, okay, maybe you get 4 errors per cache line. Does it really make sense to protect your entire memory with a strong ECC, very strong ECC? I would argue no, because the overheads of that is very high, right? Meaning I have a good idea why the errors are happening. Why not? I can design a much more efficient mechanism to correct the errors than ECC, which wastes a lot of space, right? I don't want to associate every 64 bits with additional 8 bits to protect. Does that make sense? Okay, so I think it's good to think about the efficient error correction mechanisms. Now, I have my anecdote over here is I gave this talk in a supercomputing conference talking about RowHammer, and later a very senior person from some major DRAM manufacturer, he was the next one to talk, and he basically started his talk by responding to my talk. Let's say he basically said, "We have a solution for RowHammer. It's called ECC." And the funny thing is, later works clearly showed that error correcting codes are not even good enough. So we clearly show that they're not good enough, right? But later works in security, hardware security, also showed that, oh, you can take an ECC DRAM module that exists, and you can actually induce an attack, and you can gain kernel privileges. And we're going to see some numbers later on also. This number is becoming worse, basically. Error correcting codes are really going to be unwieldy unless you want to add a lot of overhead to DRAM. So I think, as you can see, there's some mindset issue in industry. I understand they want to market their products, but it's good to also be a bit responsible to what's real and what's unreal. Sometimes I feel like people are denying reality, even though we know what reality is based on experiments, right? Okay. Of course, there are other examples of this denying reality that happens today a lot, but they're not as technical or as close to the subject of this lecture, right? Okay. Yeah. So there are other interesting data, like you can actually affect many cells and many rows. So it's not just the adjacent row. The interesting thing is this is called right now blast radius. Basically, you have a RowHammer attack and you're blasting something, meaning causing bit flips, and your radius can be larger than 1, meaning not just the 2 adjacent rows, but the rows that are next adjacent after that, and the rows that are next adjacent after that. So the effect of RowHammer is actually larger on the array because there's coupling that happens in the array also. Okay, this is interesting also. I mean, we're going to see some more results from 2020 that shows this effect again. That was interestingly disputed by some manufacturers, but I don't think they were correct again. Okay, so cells are affected by 2 aggressors on either side, and this is the idea of double-sided RowHammer. We observed it, but we didn't take advantage of it in this paper, basically. And Google folks picked up on it and said, oh, you can do double-sided RowHammer, basically. Okay. Okay, and this is the first RowHammer analysis paper we talked about. Now let's talk about solutions. I would like to talk about solutions, and then we can take a break. Does that sound good? Because this is a logical. Any questions so far? Any comments? Yes.
I guess it's like, it's actually a big milliseconds for a RowHammer.
Well, I don't know the exact time, basically, because clearly the minimum amount of time is really the number of activates you need to do times how long it takes to do the activate, right? To induce a bit flip. But again, our paper is old, right? Later, there have been better attack patterns that have reduced the time. I think 16 milliseconds is quite long, let's say, to get to the first bit flip, I should say. Yeah. Yeah, but that's 8 milliseconds or so, I think. Yeah. Maybe that's the case. Yes.
I guess I'll get worse because I think one of the so that will like bring down.
Exactly. Yeah. Yeah. Exactly. If you improve the latencies, this problem becomes worse, right? As you scale the technology, this problem becomes worse. So there's no winning. Basically, RowHammer is clearly poised to become worse, right? If you think about it that way. If you want to improve performance, you want to reduce latencies, that reduce the activation interval. That leads to more activates per refresh interval. Yeah, but I think those numbers change basically over time also because of better hammering patterns. And we will see that that was a number from 2014, right? In fact, we started doing the studies in 2012, as early as 2012. So those numbers are actually relatively old. I will give you new numbers. A new number is going to be much lower. Basically, you can induce bit flips after 4,800 hammers to 2 rows. So 9,600, almost 10,000, let's say, RowHammers. Okay. Okay, and you can do the calculation, right? Okay, 10,000 RowHammers. Each RowHammer, let's say, takes 50 nanoseconds. That's 50,000, 500,000. That's 500 microseconds. That's 0.5 milliseconds, right? So that's much worse today. It's going to get worse also. Okay. Does that make sense? Okay. Okay, so let's talk about solutions. So clearly, RowHammer is a problem that affects existing chips as well as future chips. And solutions need to be a bit different because immediately you need to protect the chips because they're vulnerable in the field. Clearly, you have limited possibilities because chips or memory controllers or the systems are not designed to basically protect for errors like this. In fact, they're not even designed to protect for any error in DRAM today, right? Because most DRAM that you have in consumer devices, almost all DRAM, doesn't have any protection, no error correcting codes. Now that has changed recently. DRAM manufacturers are adding error correcting codes inside the DRAM chip. So that's changing. But again, that's not enough for RowHammer, I would argue. It's able to detect single errors, basically. Okay, so there are limited possibilities over here. But longer term, I think you have a wide range of protection mechanisms, and your creativity is the limit over here, basically. You want to protect future DRAM chips. And we discussed both types of solutions in the paper, actually. But there's been a lot of also healthy research in this area, which we may cover later on. But the first paper proposed 7 solutions in total. And I'm going to describe one of the solutions that have had a lot of impact, actually, that I believe is still interesting and important. Maybe it was not implemented as good as it should be, let's say. But these are some potential solutions, right? Make better DRAM chips, meaning, there are many options over here, right? Like isolate the rows better, use different types of material that's less vulnerable to this disturbance, use different devices, and people propose different things. But of course, almost always the cost is a big limiter over here. We came to this place because we are able to scale what we have very nicely, and that start inducing these errors clearly. If you change the materials, there's a huge cost, basically. And you can review our paper that talks about some of these. Refreshing frequently, we discussed this. This is not good for power and performance. Sophisticated ECC, I think we discussed it. Again, cost and power. Sophisticated ECC can prevent the errors, no question about that. I think refreshing, just like refreshing frequently can prevent the errors, but it's very similar to ECC and refresh are very similar, right? These are two very general purpose error correction mechanisms. ECC being even more general purpose than refresh, right? Refresh corrects errors that are leakage dependent. ECC can correct any error, right? Your bit flips, I don't care why it flips. As long as my redundant code can fix it, it's fixed, right? So that's why ECC is very general. But I think these have similar downsides. It should also be power. I think ECC also consumes power. ECC also reduces capacity, right? Because you're wasting some capacity. That's why we said these solutions are not good enough. We kind of dismissed the access counter solution, which I think it's good to revisit. And I think it's being revisited also. But basically, the way we envisioned it, access counters could also be very costly. And that is true, actually. Basically, what is the idea of access counters? You keep track of some access counters, you figure out which ones are the frequently activated rows, and you refresh them, refresh the victim rows, meaning physically adjacent rows to the aggressor rows that are frequently activated more often, once in a while. Basically, you have targeted refreshes to those, let's say, victim rows that you guess are victims, because you know which rows are frequently activated, right? So you can do the solution in software, not as reliable. You can do the solution in the memory controller, probably more reliable. Because in software, you don't have enough visibility into what is being accessed, right? You need to have hardware counters to add that. So the downside, of course, figuring out what is frequently activated, right? And that's, there's a lot of interesting algorithmic work over here, I think. For example, in our latest work, we use Bloom filters, multiple counting Bloom filters to actually figure out what is frequently activated. And I think that's a good solution toward, but again, it's costly, no question about that. So everything here is true. Cost, power, complexity is true. but I think this may be a good solution to continue examining. In our original paper, we kind of dismissed it, saying that it's very difficult to do. And it is difficult to do, but it doesn't mean that we shouldn't really examine it. Because this is, again, targeting the solution to the problem, right? Refreshing frequently is not doing it as much. ECC certainly is not doing it. But access counters is really trying to find the access pattern that's malicious. It's trying to basically get rid of that access pattern or get rid of the effects of the access pattern, right, by refreshing. So if you have access counters, you can use it for multiple purposes, meaning you figured out which ones are the frequently activated rows. One option is to refresh adjacent rows, right? Another option is to say, oh, I see that this row is being frequently activated, so I'm going to reduce the activation rate of that row, meaning throttle the access to that row. So that's another solution. If you know which ones are frequently activated, you can take different actions. And our recent RowHammer paper actually has this second approach. Maybe there's a combination of approaches. Okay, but very naive solutions like throttling accesses such that you limit the access interval or limit number of accesses don't work very well. Very high performance overhead. Refreshing more frequently doesn't work very well, at least if you want to get rid of all of the errors, right? Yeah. Okay, so what is implemented? Basically, the immediate solution that was implemented is really refreshing more frequently, but not at 7x, it's 2x or so. Well, this is Apple's patch, basically. You can read this release. They basically said they mitigated the RowHammer issue by increasing memory refresh rates. Of course, like Apple would do, they didn't tell anything, right? Meaning they didn't tell how much they increased the memory refresh rates. The guess is about 2x. And I like this. I like what they did because they actually credit the original work that led to their solution. And we actually proposed a solution, increasing refresh rates. I mean, that's an obvious solution, right? There's nothing to propose over here, but it's something to evaluate. Okay, other folks also released, well, basically everybody released this patch. I'm going to show you some examples from Intel memory controllers. Yes?
So the thing you just showed, they talked about RowHammer and RowHammer.
Yeah.
They cite the original work,
Huh?
which doesn't talk about RowHammer.
No, we do talk about RowHammer. So if you look at footnote, was it footnote 1? Yeah. Yeah, exactly. So I mean, so we did work with Intel on this work, and so we've been working with them since 2011, 2012 on this problem. So Intel, during the course of research, filed some patents that talk about RowHammer. We didn't want to use that word necessarily in the paper, but yes, we referenced some patents that talk about RowHammer, right? So it became famous as RowHammer because it's a good name, right? But yes, the original paper didn't really call this a RowHammer, right? We called this DRAM disturbance attacks. But it became more famous as RowHammer later on. Does that make sense? Okay, cool. Okay, so basically our solution was, I think, actually very low cost. And I think there's room for improvement in the solution. It's a probabilistic solution. And that's one downside. It's not deterministic. Basically, the idea is very simple. Memory controller or the DRAM chip internally. We propose memory controller because memory controller is better from our perspective. It has more control. DRAM chip is right now, let's say, a slave. It's harder to fix the problems inside the DRAM chip. If you change the DRAM interface, the memory controller can be on the DRAM chip also. But basically, after closing a row, you activate, meaning refresh, one or more of the neighbors with low probability. Very low probability in this case. You can see 5 out of 1,000 times. And if you pick the probability nicely, you can get rid of all of the errors, right? So we say that the reliability guarantee is very strong, and by adjusting the value of P, you can vary the strength of the protection. So by being more, if you're more paranoid, you can set P to 1, right? Every time you close a row, you refresh its adjacent rows. Probably a bad idea, right? You don't need to do it that frequently. This, of course, depends on the hammer count that leads to bit flips. If your hammer count is like 139,000, like we show in the original work, the probability can be lower. If the hammer count is 9,000 or 10,000, like we show in more recent work, the probability needs to be higher, right? So, yeah, and you can see that at least for the hammer counts we examined in 2014, the performance overhead is very low, and it's stateless. Basically, you don't need to keep track of anything. you just basically flip a coin. It doesn't need to be random, in my opinion, also. Of course, security properties need to be analyzed if it's not random. Or even if it's random, security properties need to be analyzed still. But basically, you just refresh based on this probability. And that's what we argued, basically. And I still like it, actually. I think there's more room for improvement. Of course, there's been 7 years. There's people have found out other things. But you could implement a DRAM chip, as I said. Why? There's slack in timing and refresh parameters, meaning manufacturers are, even though, for example, refresh takes 100 nanoseconds, let's say, they specify it to be 300 nanoseconds. That's an example. I just made it up, right? So there's plenty of slack today, that, as we have shown, as we will see also in later works. Meaning, whenever the manufacturers, whenever the memory controllers issue a refresh command, don't just refresh what you were going to refresh anyway, but refresh some more, meaning some victim rows internally, probabilistically, right? That's the idea. Maybe some recently activated rows, right? You can keep track of them in the DRAM chip easily, but you don't need to keep track of frequently activated rows. Recently activated rows, keeping track of them is easy. Last row, for example. But frequently activated rows requires frequency counters. Your algorithms need to be completely different. So you can use the slack today. In fact, this is what manufacturers are doing. In our recent paper coming up at Micro, we discovered that even though the refresh rate is specified to be, let's say, every 32 milliseconds, internally, DRAM is refreshing much more frequently by reverse engineering what's happening internally in DRAM. So they've added this protection internally also. They've added other protections. And even then, you can bypass all the protections, as we will see a little bit. Because fundamentally, they're not designed to be secure enough, I will argue. Okay. Okay, if implemented in the memory controller. Oh, there's a question. Okay, let's see. Okay. Okay, basically, I guess if you're doing it on the controller anyway, you could also implement an opportunistic para where you increase P for things of high importance and decrease P for low importance data. Absolutely, yes, yes, yes. So basically, I mean, of course, I think that's a good idea. I like it. Basically, security critical data gets higher priority in this sort of protection. But of course, that requires you to communicate security critical data to the memory controller now, right? And we discussed this last time. You don't know enough even about allocated data, right, in the memory controller. But I like the idea for sure. I mean, you can certainly do that if it was a good design, let's say. Okay, so if you implement in the memory controller, then I think it's easier to do. And also, I think this is what we argued for. You need to have better coordination between memory controller and DRAM, just like the memory scaling papers you're reading. But of course, in this case, memory controller should know which rows are physically adjacent. And a better interface would help here, right? You don't want memory controller to physically reverse engineer everything, and it may not still have perfect information in that case. But the good news is, before DRAM manufacturers came and said, oh, we have a solution, RowHammer is fixed, Intel used to have this solution, meaning probabilistic activation inside their memory controllers. It's a variant of the solution. It's not exactly like what we envisioned. It could have been done better, but they were actually moving in the right direction, let's say. Meaning memory controllers was becoming a little bit more intelligent. So in the BIOS of an Intel system, you could pick your RowHammer solution, either hardware RowHammer protection or 2x refresh. And hardware RowHammer protection is some probabilistic adjacent row activation, basically. You can fix your probability, basically, you can see over here. It's nice, I think. I mean, that's not what we envisioned clearly, right? You want to do this dynamically, like your colleague mentioned. Memory controller should do it transparently to the user also. Maybe user provide some guidance, but maybe BIOS is not the right place to provide that guidance, etc. But it's a step in the right direction, I think. But of course, until the manufacturers said, oh, we have this problem solved, trust us. And then Intel basically turned off these protections in their memory controllers. So we will talk about that in the rest of the lecture. Okay, so basically, I think I would argue that main memory needs intelligent controllers for security. I mean, industry is writing papers about it too, but they didn't write about RowHammer, as we discussed last time, right? They did write about DRAM scaling issues, but they did say we should co-architect controllers in DRAM, meaning make controllers more intelligent. Maybe they had RowHammer in mind because at the time this work was published by Samsung and Intel, it was published at the same conference where we presented the RowHammer paper, actually. So they knew about the work, but they couldn't write about it. They couldn't even talk about it for some time, actually. Okay, and we have intelligent controllers for NAND flash, for example, which we will talk about in some other lectures. But if you look at NAND flash, the controller does a lot of things. like fixing retention errors, fixing read disturb errors, fixing many other errors. And if you're interested, at some point we may actually cover some of these really interesting issues that happen in flash memory. Okay, so let me go quickly to finish this part of the lecture. But basically, we've written other papers saying that this problem will get worse. This is a retrospective paper that was invited to a hardware and embedded security issue. Basically, we discussed a lot of work leading to, about RowHammer that happened between 2014 2019, and we argued for this, of course. So in the later part of this lecture, what I'm going to do is really talk about what happened more recently. Basically, we didn't. So what happened? Clearly, there was a lot of work that happened in security, like we've seen, analysis. But we didn't do a lot of characterization in RowHammer. We were looking at a lot of other things. We said basically this problem, this needs to be solved. And we hoped that it would be solved, basically. But we saw this claim from manufacturers saying that, oh, we solved the problem. And that was interesting to us, basically. And at that point, you should, as a researcher, it's good to say, is this really true? So especially if someone says, oh, I solved the problem, and I'm not going to tell you how, right? That's not good for security. Whenever you have a good security mindset, you should really say, okay, I solved the problem, and here's how. Attack it, and show me how I can really solve the problem. Right? That's how it really works in general. So we're going to talk about some works that revisit RowHammer, that basically show that the claims are false, and that also try to find better test patterns for RowHammer. But it's interesting that, I mean, there's RowHammer research is still going on. There are a lot of things to examine. This is actually one session from IEEE Security and Privacy, and its title is RowHammer. I'm going to later, if we have time, show you the reviews that we received for RowHammer later on, saying that RowHammer is not interesting, basically. Apparently, it's interesting to some people. Okay, we're going to talk about more solutions. And there are two upcoming RowHammer papers at Micro also that go into even deeper insights that I will briefly mention in the remaining part of this lecture. I believe there's more to come, basically. We're not at the end. Until we really solve the problem is not solved, right? And a problem is becoming more difficult, basically. That's why the solutions are going to need to become more interesting, basically. I think we're at a point, because I think we kind of, at least the industry did not develop the solutions well enough over the course of, let's say, 8 years. So we really need to develop real solutions to the problem. Okay, that brings me to the end of the first part. Any questions? Yes, please. Is this thing still not working when you press? Oh, okay. Okay, keep going. I'm going to try to. Yeah, I'm listening to you with one of my. Uh-huh. That's a good question. Yeah, I think there's some assumption, but I mean there's some activity factor also. I don't think it's looking at. Yeah, actually I don't know. I don't remember. Huh? Yeah. So certainly, I think that was a good direction because in the memory controller, I think you can actually understand these mechanisms better. But again, that's also vulnerable. The implementations were vulnerable, basically. Even the para implementation was vulnerable with Intel. Exactly. I mean, if you want a fully secure system, you don't want a good enough concept. You also want a good enough implementation that prevents the problem, right? I think a lot of the implementation, even the on DRAM implementations today that are hidden to us, they have some good ideas, but they're not proven to be secure, basically. They're just assuming some things. And they're basically assuming that the attacker doesn't know anything about what's going on underneath. But of course, taking this course, you know that if you want to solve a problem, and if you're an attacker, your problem is knowing what's underneath, right? From the attacker's perspective, that's a perfect target. Somebody's not telling me something, I'm going to figure it out. And they will figure it out. So that's the problem, basically. Your implementation needs to be fully secure. Yes? So I'm not going to be as aggressive to claim that para is the only solution, basically. I think para can solve the problem if you increase the probabilities, especially today's hammer counts, but that's not a good solution also, right? Because you're refreshing a lot right now. I think the concept of para is useful, but it could be perhaps augmented with something else, like maybe throttling a little bit, trying to identify these excesses, frequently accessed rows, and throttling them perhaps. I think basically para by itself is not enough today. And I will show you that also experimentally. Yes. Could you say it again? I couldn't hear very well. Sorry. Like what is the exact approach you have in mind? I see. I see. Basically, you want to disable some things at the architectural level so that. Yeah. Yeah. So that's a good point, basically. Basically forbid some hammering patterns, let's say. I will say it that way. Yeah, I think that's potentially you could do that maybe, but then you'll have to forbid all possible hammering patterns, right? And there are many possible instruction sequences that lead to hammering patterns, as we show in this one of the basically in this work, if you're interested. So there are many possible instruction sequences that lead to these hammering patterns. You'll have to find out all of them and basically forbid all of them. So I think fundamentally, I think that's a hard solution. Yeah. Yeah. Okay. That I think what you say assumes that this is useless, but there are some programs where this could be useful. Meaning, okay, I think that brings us to the question: is RowHammer just a security problem, or do real applications also have these patterns? And it turns out there's a very small fraction of real applications that lead to this sort of hammering patterns. And as the number of activations go lower and lower, as technology scales, more and more real applications will cross to that domain where they will look like RowHammer attacks, basically. So I think that solution is tough. Not only tough, but also, I think in general, forbidding some things is a harder thing to employ. People will also figure out how to circumvent those. Sure. Yes.
So far we're talking about technologies
Yeah.
We've kind of been lowering voltage, right? Power.
Yeah.
I was thinking like it kind of has opposite effects. Because on one hand, the threshold is lower. The threshold is lower, then also it has effects.
Yeah.
Yeah.
Yeah, I mean, certainly that's something people are looking into, how voltage affects RowHammer. And I don't think there's any published work yet, but absolutely, there's some effect over there. And I think the effects are, as you said, right? It could be better or worse also at the same time. The question is how bad it is, right? Yeah, not yet. Yeah, not yet. Maybe next year you will see some work. Sure, but that's a very good question, basically. There are many parameters also, right? That we have not fully examined yet, and they're coming up right now. Like this work looks at temperature, for example, in a better way, in a more methodical way, and also spatial variation of the vulnerability. It basically shows that some parts of the DRAM are much more vulnerable. So that could be useful for protection mechanisms, right? If you know which part of the DRAM is much more vulnerable, you refresh it much more frequently, for example, if that's your solution to RowHammer. So it can reduce the overheads of some of the protection mechanisms, understanding what's going on underneath. Okay, if there are no other questions, this was good actually. but we should probably take a break. Okay, let's take a 16-minute break like usual. Come back at 3:06, and then we will continue with part B of the lecture. 64 milliseconds. Let me see. Hello? They can hear me? Okay, that's good. I cannot hear them. Say it again? Oh, okay, maybe not. I am sharing the screen, right? Okay, I see. So the live stream is also working fine? Okay. What do you mean? Oh. Why not? It's a good question. Maybe it's a little bit delayed. Yeah, I think it's a bit delayed. Okay. Okay, cool. Now I see it. What do you think? Okay, thanks. Wow, all these reliability issues, as you can see, they're real, right? I don't need to convince you of how big of a problem reliability and security is, hopefully. Yeah. Yeah, I think it's going to get worse, basically. I don't want to be the bearer of the bad news, but if you don't do something about how to build dependable systems, I think we're going to have more issues going into the future. It's just very hard to trust these systems with our lives, right? We cannot even make internet work very well. Okay, that was lecture break, I guess. Okay, now we're going to move into more recent RowHammer. And I think there's a lot to do in this area still. I think it's quite exciting. But let me give you a few works that happened more recently, like in 2020. And since you're taking the class right now, hopefully you get exposed to the most recent research, even in 2021. I think there's going to be more. Okay, we're talking about this. We talked about these, and I mentioned some of these works. Okay, and I'm going to go into trespass work that we did more recently. I think this is fascinating. As I mentioned, DRAM manufacturers introduced these in DRAM RowHammer mitigations, generally referred to as target row refresh. Remember the 2014 work from the Memtest 86 company? They mentioned, oh, DRAM manufacturers and JEDEC. JEDEC is the standards corporation, basically, that gets together all the DRAM manufacturers and other people. And they basically say that, they were saying in that work that, in that website, that this is going to be a solution, right? And it was touted as a solution. But of course, they didn't tell the world how they fixed the problem. And I think anytime you come up with a solution that's not secure enough, people will attack it and figure out ways to circumvent it, let's say. Okay, basically what's trespass? Basically, this is the first work that showed that TRR protected DRAM chips are vulnerable to RowHammer in the field, despite the claims that DRAM chips are advertised as secure, right? And this is actually very clear. You can find big flash news saying, "Oh, we manufactured RowHammer free chips." So I'm not exaggerating any of these claims, basically. I think there's a danger here, and we can like you really want to be sure when you advertise something, but I guess you can get away with a lot of things these days. Okay, basically, this work introduces the many-sided RowHammer attack. We'll discuss why that is interesting. And the goal is to really circumvent the internal protection mechanisms, right? For that, you cannot just do double-sided because internal protection mechanisms can detect two rows that are being activated, hammered. But internal protection mechanisms, basically the idea is that internal protection mechanisms have limited capacity in terms of how they detect hammered rows. And if you can somehow fool them so that they cannot keep track of all of the rows that you're hammering, you can basically cause bit flips. That's the idea. So basically, hammer many rows to bypass the internal protection mechanisms by overflowing proprietary tables that detect aggressor rows. If that table has only 4 entries that can keep track of 4 rows that are being hammered, maybe if you keep hammering 5 rows, you will overflow the table. As a result, you can actually induce bit flips. That's the idea. Makes sense, right? Hopefully at an intuitive level. And basically, the goal was to reverse engineer the TRR and PTR as a probabilistic TRR. That's essentially similar to PARA, implemented by Intel at that time, right? Mitigation mechanisms implemented in DRAM chips and memory controllers. So TRR is in DRAM chips, PTRs, and memory controllers, as we discussed last time, right? And provides an automatic tool, but it doesn't perfectly reverse engineer. Basically, we have a good idea to provide the attacks and make the attacks work, but we don't exactly know how the mechanisms are working underneath. Right? Yes. Maybe you can press that one since you solved.
So the revisiting RowHammer paper mentions PTRR as a pseudo TRR. So is this the same as?
I think so. Yes, it's the same.
Same as para.
Well, I wouldn't call same as para, right? It's an implementation that's inspired by para. Again, this is also not documented by Intel, but it's doing something probabilistic. Does that make sense? I wouldn't call same as para, but it's pseudo TRR is inspired by para. Okay, so this work also provides an automatic tool that can effectively create many-side RowHammer attacks in DDR4 and LPDDR4 chips, the low-power versions of DDR4, basically. And this is nice, actually. The tool is released, so you can actually do your own experiments. Other folks have used trespass tool to generate RowHammer attacks. Okay, that's the high-level summary. Now let's go into a little bit more detail. I don't want to spend a lot of time, but I'm happy to answer questions, of course. And this is one of the papers that is extra credit, I think, if you're interested in doing it. But these are some patterns that trespass employs and it looks at. Basically, this is double-sided hammer, clearly, upper part, but also it used assisted double-sided. It hammers one more row. And you can circumvent a protection mechanism this way. You can read the paper for more detail. This is four-sided. The red ones are aggressor rows. The victim rows are in blue, as you can see over here. And you will see there are 9-sided, 13-sided, 19-sided attacks, meaning you're hammering many, many rows so that you can basically overflow the internal tables or some random sampling-based mechanisms that they have internally. We don't exactly know how they exactly operate, but you can overflow them, basically, or overcome them, let's say. So how does TRR work? Target row refresh. Basically, it's a high-level idea. It's in the documents, but it doesn't talk about implementation at all. Basically, you track activation count of each DRAM row. Each is, of course, a very strong word, right? Some sample DRAM rows, probably. And you refresh the neighbor rows if row activation count exceeds a threshold, so that you don't get a RowHammer bit flip. So fundamentally, it's not a bad idea, but of course, the devil is in the details, how you really implement it. Right? It's an access counter-based mechanism, basically, like our original RowHammer paper described. And we said that this is difficult to make it work. And I think we were right from that perspective. So there are many possible implementations in practice. And basically, the way folks tried to achieve this was through obscurity, meaning, okay, we're not going to tell you how we are doing it. And in DRAM TRR is an implementation of target row refresh that's embedded in the DRAM chips, not exposed to the memory controller. So certainly you could do this in the memory controller as well, like, right, fundamental idea. So this is what happened in terms of timeline. So Intel first deployed this, let's say, pseudo TRR, in the memory controller. And then, even earlier DDR4 mechanisms were protected using memory controller. But this is also vulnerable. I'm not going to go into details of it. But then later, DRAM manufacturers said, okay, we've solved the problem, and we have in DRAM TRR, that's RowHammer free. And this is where we actually really focus on in this paper. And the goal was to understand how in DRAM TRR works, at least partially, or at least good enough to induce bit flips and bypass the protection. And this is how we do it, basically, with a new RowHammer pattern. And we see hammering up to 20 aggressor rows allows bypassing TRR. Yes?
I'm sorry, I don't get the timeline. Like you say there's like in 2013. Isn't your paper from 2014?
Yeah, but remember, we were working with Intel from 2011 to 2014. So Intel actually, if you look at the paper, they're co-authors from Intel. Yeah, exactly. We basically work together so that they can also put the solutions. So that's a good way of working, I will say. But I mean, their solutions were not, let's say, it was in the right direction, but it didn't. It wasn't good enough. Also, maybe at the time it was good enough, but maybe they could have improved over time until this point where they were told we have RowHammer free chips, basically, right? Yeah, so it's good to keep that timeline in mind. Okay, sure. Okay, and hopefully this enables us to automatically test memory devices also using trespass. Actually, this is a tool. It's a fuzzing tool, basically. It tries to figure out different access patterns and hopefully enables automating hammering pattern generation. It requires more work, but and we didn't use it to its full capacity, let's say. But even then, the results are good enough, let's say. It basically shows that you can induce bit flips in these TRR protected chips. Okay, so basically we heavily make use of our FPGA-based infrastructure that we discussed to understand what's going on in the DRAM chips. And that's the soft MC infrastructure as we discussed. So this is our hypothesis as to what in DRAM TRR looks like. Of course, we don't know exactly, but basically there's some sampler and there's an inhibitor. Sampler is trying to figure out what are the frequently accessed rows, and inhibitor is refreshing neighboring rows, right? So to figure out what are the frequently accessed rows, you need to track aggressor row activations clearly. And there could be multiple different ways of doing it or combinations of different ways, right? For example, you can have frequency-based, meaning record every anti-activation, sample it. Record first n row activations, time-based, and random seed-based, meaning record based on a coin flip or some random number you generate, right? And all of these are actually employed in some manufacturers. In fact, our latest paper at Micro that talks about uncovering TRR goes into a lot more detail into the existing mechanisms, and we may have a lecture about that. I don't intend to talk about today. But regardless of the mechanism, you have a limited size, right? How many rows do you keep track of? And if you can somehow overflow this, then you basically can potentially induce bit flips because the sampler may not have recorded an aggressor row that you're really hammering, right? That's the idea. An inhibitor prevents bit flips by refreshing mixture rows clearly. But of course, inhibitor is also limited in terms of how many refreshes it can do. Meaning, so remember, this is done in DRAM. And externally, memory control is sending refresh commands, right? We discussed this earlier, and it's sending refreshes periodically. And as I mentioned also earlier, there's some slack time available in the refresh window, meaning refresh interval between two different, how long the refresh should take, basically. That's the latency of regular refresh command. And manufacturers are piggybacking on the slack. Okay, I refresh whatever I should refresh, assuming everything should be refreshed every 64 milliseconds. Now there's some slack time remaining, and the memory controller is assuming that refresh is still taking place. I can use the slack time to refresh some of the victim rows that are detected by the sampler, right? That's the idea. So it has a limited slack time clearly. Okay, so keep that in mind. So basically, you can, if you have an FPGA-based infrastructure, you can construct different kind of access patterns to try to answer some of these questions, basically. Like, how big is the sampler? For example, you can pick n aggressor rows. You can perform a series of hammers, 8K activations. And for each series of hammers, you issue R refreshes. And by changing n and R, you can try to figure out how many bit flips you're getting, right? That's the idea. And you can do this only with an FPGA-based infrastructure. In a real system, you cannot basically, even if you may have control over the hammers, you may not have control over the refreshes, right? In fact, you don't, because the memory control is automatically issuing the refreshes. But with our FPGA-based infrastructure, we have control over both of them. We can issue refreshes whenever we want. We can turn off the refresh, right? We did those studies that we discussed last week. So that's what this infrastructure enables. That's why it's so powerful. So with this infrastructure, you can do attacks like trespass, let's say. So okay, let's basically vary these. So this is the experiment. We're going to change the number of rows we're going to hammer, and we're going to change the number of refreshes we issue to a sample bank, let's say, from vendor C. So this is x-axis. This is the number of aggressor rows we hammer, number of refreshes we send. Okay, so if you're not doing anything, not hammering, not refreshing, you should not expect bit flips. That's good, right? That's why these are all zeros. I don't know if you can read that, but they're all zeros basically. So if you're hammering an aggressor row, but not sending any refreshes, you probably should expect bit flips, and that's what we're getting. We're getting some bit flips, right? 2. Okay, you could argue it's small or high, but it's only one row, single-sided hammer. Okay, well, this is a mind of its own, or pressing something. But basically, if you're hammering 2 rows, and if you're issuing 1 refresh, basically you're reducing the bit flips. It's going on its own. Maybe I should just So basically, the first observation is that TRR mitigation acts on a refresh command. If you're not issuing refreshes, bit flips will keep increasing, basically. That's the idea. As you can see over here, if you're having 2 rows, not issuing refreshes, you get a lot of bit flips. But if you're having 2 rows and issuing 1 refresh, you're getting 1 bit flip. But if you issue 2 refreshes, you're getting 0 again. Make sense? So as you keep issuing these refreshes, victims are getting refreshed. That's the idea. Now let's do it for more rows, 3 rows. Now it's becoming interesting. The mitigation mechanism can refresh only a single victim within a refresh operation. That's what we observe also. If you issue 1 refresh, there's only 1 victim being refreshed. That's why the bit flips are like this. Okay, you can read the paper for more detail. Okay, but okay, let's look over here. We have 4 aggressor rows that are being hammered. We have 4 refreshes per round over here. At some point, you can get the sampler size. You can basically see that issuing more refreshes are not giving you any more benefits. So let's take a look at that point over here. You have 4 aggressor rows, and after you do let's say 4 refreshes per round. Okay, maybe this figure is better. You do 4 refreshes per round. The number of bit flips stabilizes, right? Hundreds. Again, here you have 5 aggressor rows. You issue 0 refresh, 1 refresh, 2 refresh, 3 refreshes per round. Once you get to 4, the number stabilizes. Again, 6 aggressor rows, bit flips increase, but once you get to 4, the number stabilizes. That's true for all number of aggressor rows over here. So this basically tells us that there are probably 4 rows being kept track of, meaning you're refreshing 4 victim rows, let's say. That's the idea over here. And I think this is quite powerful, and I don't think how you can do this without any other infrastructure. And that's the idea, basically. Now we have kind of revealed that the size of the sampler may be 4. Of course, there may be something else going on, but this is good enough for us, right? Now we have some hammering patterns, right, that we can use. Okay, so these are some observations that I've already mentioned over here. Sweeping the number of refresh operations on the aggressor rows while hammering reveals the sampler size to you. Of course, it's not always easy for every vendor because every vendor has some slight differences. That's why it's not going to be as effective for every vendor, but we're going to be able to circumvent some chips from every vendor over here. Our newer paper actually circumvents essentially all chips as long as you put enough effort into it. At least that's our claim. Yes. Exactly. Exactly. Yes. Basically, we're issuing it's the same refresh command. Basically, there's nothing special. We just need to issue them. Yeah. But we're issuing them in specific times to understand what's going on underneath. So we're not using the regular refresh schedule. Exactly. But we're using this infrastructure to really understand what's going on. And then I'm going to show you from real system results that we're going to take what we learned from this infrastructure and we're going to hammer on a real system and show real bit flips. Yes.
A sample size of 4 sounds incredibly small. Why would vendors choose to choose?
So that's a good question. Basically, hardware cost, right? I think this is a per bank sampler size. So every bank keeps track of 4 rows. It's small, yes. Basically, DRAM manufacturers are frugal. They claim that their hardware cost is their bottleneck, right? And if your cost is a real concern, then yes, that's how you set it. Yeah, but I would argue that it's small also, yes. So I think the trade-off is really which one's more important to you, hardware cost or your security or reliability. Yeah.
Isn't the simpler buffer probably also just a row of cells or a row of like transistors?
Could you say it again? I couldn't.
Isn't the buffer just the same kind of chips as the rest?
No. So the buffer is not DRAM. The buffer is really SRAM. So basically, that's why it's high cost. It's really SRAM logic, and implementing it on a DRAM chip. Whenever you put SRAM logic in a DRAM chip, it's actually not good because the process is not optimized for logic. That's the main reason. But again, I mean, one could argue that this is such an important problem that 4 is so small, right? And I agree with you. Okay, so this is based on a real system, actually. This is where we're actually issuing refreshes as specified by the data sheets. That's the refresh interval, let's say, every 7.8 microseconds you need to issue a refresh such that everything gets refreshed every 64 milliseconds in the end. That's how it works basically in DRAM. But you can see that by hammering 5 aggressor rows, you can get a lot of bit flips. I don't remember this is in the bank. I think this is one bank. That's why the bit flips are low. You can read the paper. But the point is you can get bit flips. And every single bit flip matters, actually. There's some security work showing that even if we get one bit flip in a very predictable manner, you can potentially circumvent the system. So even one bit flip is too much, let's say. And we're getting more than one. And you can see that it's kind of odd, meaning as you get to 6, you don't get bit flips. That's weird. 7, 8, 9, 10. Okay, 13. There are some real system effects that are going on with that we don't quite understand also, right? I mean, clearly, there's a trade-off here. If you hammer too many rows, the number of activations you do in each row is lower, meaning the probability that you're going to cause bit flips is also lower. But if you have more rows, then the likelihood that you're circumventing the mechanism is also higher. But this doesn't; those two trade-offs don't quite explain this picture, right? So there's clearly something we don't understand. But the point is, there are some hammering patterns that lead to bit flips, meaning TRR doesn't prevent them. It's not RowHammer free. Yes.
This kind of can ask earlier, which is if you're increasing the amount of rows you hammer, you also reduce the amount of hammers you get in before a normal refresh comes in.
Exactly.
So isn't there technically an upper limit to how many you can hammer, and therefore also a unpassable limit for the amount of for the size of the sampler where it's always going to be able to block a RowHammer?
Yeah, exactly. I think now you're thinking more methodically in terms of how you could solve the RowHammer, right? You need some size of sampler, and there's an upper limit for the sampler size. I agree. Yes. Yeah, I think if you do the calculation, I mean, too expensive depends on what cost you can tolerate, how important the problem is. But yes, it's a high number basically, and the number is increasing, as I will show you later, because the number of hammers you need to do to get a bit flip is reducing. Yes, but I like that's the mindset basically. What is the maximum thing that you need to prevent? Yeah. Yes.
The solution we just talked about.
At different frequencies. Yeah.
It's a mess.
Yeah. Sure. Exactly. Yeah, exactly. I think how do these things interact? Yeah, now that becomes more difficult. That's why you need an intelligent controller that can figure this out relatively. I'm not going to say it relatively easily, but you need some intelligence in the memory controller to make these things work nicely. And flash memory controllers are actually quite good at that today, let's say. They can always be improved, as we will discuss as well. But yes, now if you start combining, okay, let's do RAIDER, heterogeneous refresh rates, while also having RowHammer protections in place. How do they work together? While also reducing latencies, as we will discuss. How do they work together? That's why you need to have a memory-centric thinking, basically. That memory control becomes extremely important. Yeah. But very good observation. Okay, so basically these are real system results from other vendors also. I mean, I picked some of them, but the paper has others as well. But you can see their trade-offs, but you can circumvent many of the chips that we have examined. I'm not going to say most of them. You can see the number over here. I think we were able to circumvent 1/3 of them. I think we could have done better if we spent more time, of course, but it's a matter of time. It's also a matter of understanding. We didn't have enough insight into the mechanism, but it was good enough to disprove the claim that these chips are RowHammer free. Okay, so you can see the chips, modules, etc. You can see in some cases the best pattern is 19-sided, meaning you hammer 19 rows to circumvent. In some cases we weren't able to figure out. Our newer paper actually figures out much more, let's say. Okay, I'll let you read the paper. And then there's also a system level study where we actually really attacked phones and found patterns that would lead to bit flips, that would lead to attacks essentially, that makes your phone vulnerable. Again, you could argue that, okay, not all of them are vulnerable. Yes, we don't have good enough understanding to make this work on everything. And we also have limited time, right? I should say our only goal in life is not this. There's a bigger goal. If your only goal in life is to really get to people's private data, you could do it, I think, I would argue. This is a proof of concept in the end. And there's some results that show basically, these are full system level results, time to find the first exploitable template on 2 sample modules from each DRAM vendor. And you can see they're relatively small. Yeah, so you can see also the experimental methodology in the paper. And these are the time to actually make the attacks work. And these are different kinds of RowHammer attacks. You can read the paper. Page table entry attack is what we discussed, kind of, at least a primitive form. Basically, you can take over the system, let's say, in 2 seconds or so. Not bad, I think. Okay, so basically, this is the key results. I think I mentioned this about I think this is 1/3 or so of the modules. We showed them to be vulnerable, and there are different kinds of attacks needed for that. And a significant fraction of the mobile phones we test are vulnerable. These are LPDDR4X. It's a different kind of chip, but still. And I think these results are scratching the surface. The tool is not exhaustive. There's a lot of room for uncovering more vulnerable chips and phones. And we said that also in the paper. And we believe that, and we worked on it. And I think right now we have a much better understanding of how underlying mechanisms work. And we'll discuss that later. But the key takeaway is that RowHammer is still an open problem. And I think security by obscurity is likely not a good solution, at least by itself. But I think being open about this is much better. And I'll invite you to read the paper if you're interested. Any questions? Yes, you go first.
It's not really an interesting question, but I was wondering, how do you target rows on a cell phone? Do you have the APIs to the
Yeah, I think.
How?
Yeah, essentially, I mean, there are a lot of works that show that you could reverse engineer the virtual to physical address mapping and the physical to DRAM address mapping. So you really need to have that infrastructure for reverse engineering. And again, fooling the operating system to allocate things in the right place. There are some works that, like the Drammer work, right, that I mentioned, does a lot of that. It has to do all of that. So there's no existing API basically. You need to hack the system. But that's a very good question. Yeah.
Yeah, for the 34%, is that just for the newer chips that claim to be RowHammer free?
Could you say it again? Which percent?
For the 34%, 13.
Like this one, 30.
Yeah,
exactly. That's just newer chips. Yeah. Exactly. DDR4 basically. Yeah. And LPDDR4. But we didn't test LPDDR4 in our infrastructure. LPDDR4 was from the phone basically. We just, with the FPGA-based infrastructure, we figured out what patterns are good enough for different manufacturers. And we basically, on the phones, we tested some of those patterns. Clearly, they're not exactly the same chips. So they may not be exactly, they may not have the exact same mechanisms, but our patterns were still useful and transferable to some chips that we didn't test basically. Okay. Okay, shall we move on to the third one? Okay. So basically, this is the third work that I will discuss. That was also in 2020. So at the same time, we were also very interested in the circuit level implications of RowHammer. Basically, we wanted to understand, is the vulnerability becoming worse? How did the system scale? And this is, again, a modern repeat of the study that we did in 2014, let's say. But it's more of a scaling study. It's much more, there are many more things that many more chips that we tested here, more than 1,500 chips actually. So basically, clearly denser DRAM chips are more vulnerable, but there's no characterization-based study that demonstrates how the vulnerability scales. And if you don't understand how the vulnerability scales, it's very unclear if existing mitigation mechanisms will remain viable for future DRAM chips, or how you should scale the mitigation mechanisms as well, right? That was the idea. So our goal was to demonstrate how vulnerable modern DRAM chips are and how they scale, how they have scaled in the last, let's say, 8 years or so. And also study the viability of existing mitigation mechanisms on more vulnerable chips. And also predict what will happen if the vulnerability scales as we observe from experimental results, right? So it's more forward-looking study, let's say. And I think in the end, this turned out to be the first rigorous RowHammer study, characterization study across a broad range of DRAM chips. We looked at more than 1,500 chips of different types, technology node generation, and manufacturers. And there's a clear trend that RowHammer is worsening. And we also do a mitigation mechanism study where we look at 5 state-of-the-art mechanisms, including increasing the refresh rate, including para, for example, and how they're affected by the worsening vulnerability. And current DRAM chips, they have reasonable performance loss, but if the scaling continues as we have seen with experimental data from real chips, in vulnerable DRAM chips, more vulnerable DRAM chips, performance losses will be unacceptable. Even para, for example, at least para is the one that scales the best among the solutions that we examined, because all other solutions require huge hardware costs, let's say. Some of them actually, at the time they were published, it was not clear how to even change the hardware to make it work. But apparently, it's a huge performance loss, as you can see over here. Of course, this is an extreme study, as you will see in a little bit, but still, basically the conclusion is that it's critical to research more effective solutions because DRAM will be more vulnerable to RowHammer. So that's the key takeaway. Now I'm going to show you some data, let's say. Okay, I've already said this, so I'm not going to go over this again. I think I've already said this also. But basically for this, we use multiple infrastructures. We discussed the soft MC infrastructures. There's a DDR3 and DDR4 versions. These all take time to develop. Actually, in the initial infrastructure, it took us 1.5 years to develop to do the retention-based studies. But clearly, they're useful. And we also had an in-house testing infrastructure for LPDDR4 chips. That actually turns out to be very hard to build. Okay, you can see used over here. And it's tested basically. Perhaps this is the most comprehensive RowHammer study to date, let's say. 3 manufacturers, you can guess who they are. 3 types of standards, DDR3, DDR4, LPDDR4. LPDDR4 actually implements on-die error correcting codes, and you will see there are errors over there also. And 2 types of technology nodes, as far as we could figure out. Basically, you cannot easily figure out what's the technology node of a DRAM chip today because they're not advertised, but you can guess somehow. And also, we categorize things as DRAM type and node so that we can understand the scaling characteristics. I think I've shown you one result from this paper in one of the earlier lectures, but we'll see more results. So basically, characterization is important. So you need to turn off, because we wanted to understand things at a device level, we turn off DRAM refresh, calibration events, and mitigation mechanisms clearly. And of course, if you turn off refresh, you don't want the errors coming from retention errors clearly. So you need to make sure you test less than the refresh window. And we use double-sided RowHammer basically. Okay, I'm not going to go through the testing methodology, but you can guess what it is basically. You keep testing an entire row basically, and you keep doing it for every single location every single row in the bank basically. You can read the paper for more detail. These are more boring. Okay, let me give you the key takeaways. Basically, newer DRAM chips are more vulnerable. There are some chips whose weakest cells fail after only 4,800 hammers. 4,800 to one aggressor row, 4,800 to another aggressor row. So technically it's 9,600 hammers, but still that's a very low number. In 2012 through 2014, that number was 139,000, let's say. So it's reduced by some orders of magnitude, right? 2 orders of magnitude, let's say. Okay, and RowHammer bit flips happen in more rows and farther away from the victim row as well. So let's take a look at it. I'm going to go through this relatively quickly again. So these numbers are actually very interesting, right? Basically, old DRAM chips, DDR3 old, only 12% of the chips are vulnerable. New DDR3, 65% are vulnerable. And out of all the chips, we have more than 80% vulnerable. So it's similar to our original paper, let's say. But newer DRAM chips are clearly more vulnerable. We look at data pattern dependence, and we use worst case data pattern. Again, you can see the paper for that. But this is one thing that's interesting. Basically, this is hammer count and RowHammer bit flip rate. And you can see that as hammer count increases, bit flip rate also increases, as expected, right? And let's see how that scales. So this is manufacturer A, DDR4 new. This is that same curve. And this is what happens in DDR4. So basically, DDR4 old DDR4 chips. So as you go from old chips to new chips, you get more bit errors, right? For a given hammer count, you get more bit errors. And you start getting errors earlier with smaller hammer counts. So clearly, it's becoming a worse vulnerability. And that's the most consistent trend, because we were not able to test chips of all types from all manufacturers. This DDR4 old versus new is the one that's the easiest to compare. basically curve shifts up and to the left, which is what you don't want, because that's what makes the vulnerability. Basically, there are more errors at a given hammer count, and the first hammer count that leads to the bit flip also becomes earlier, smaller. Okay, I think I already said this. Makes sense, right? So that's why this is a scaling study. So row distance is also interesting. Remember this picture that where we looked at the distance from the victim row? This is we're looking at the victim row distance. So aggressor rows are plus and minus 1 in this case. Victim rows are 0, -2, 2. And if there are other rows affected, there could be other ones, of course. But you can see that this vulnerability also, there are other rows that are affected as well, right? As you can see. Usually it's the victim row that has the most errors. But in some cases, some of the further away victim rows are also affected. Okay, makes sense, hopefully. There's also spatial distribution. I'm not going to go through the results, but this is interesting because this shows how many bit flips you get per 64-bit word. 64-bit word is the protection granularity for error correcting codes. So error correcting code in LPDDR4 chips, for example, existing error correcting codes can detect 2 errors, but cannot detect 3. Meaning that if you get 3-bit flips, you can circumvent ECC, and that's what we find basically. And that's true for many manufacturers. Even though the fraction of bit flips with 64-bit words with 3-bit flips is small, they're still there. And in some cases, there are a lot, as you can see. Okay. So we also discussed this. This is scale. Actually, this is the figure I showed you earlier in an earlier lecture, right? Showing that RowHammer is a scaling problem. But the minimum hammer count required to cause bit flips also reduces in general as technology node scales. Again, I'm not going to go through the details of this figure, but this is across all of the chips that are tested from manufacturer C that are DDR4 old. So there's a distribution clearly for each chip. There's a minimum hammer count. But you can see that going from DDR4 old to DDR4 new, the minimum hammer count reduces significantly. Right? And we don't have enough data. Well, there are no bit flips actually, DDR3 old and DDR3 new. There are some bit flips. Yeah. Okay. And that scaling trend is also very similar across different manufacturers, especially for ones we have very good reliable data. The data is also something that's difficult to get in this. That's why this sort of characterization papers are really important, because industry is not going to give you this data. They're not going to talk about this at all, even. There may be some people who deny this in industry still, which is interesting, but it's important to openly provide this data also. But sometimes you cannot do much. For example, we didn't have chips from different generations for this manufacturer in LPDDR4, right? And that's true for this manufacturer for another generation. But we were able to get this manufacturer's LPDDR chips, and that gives us a scaling trend over here. Okay, another takeaway, as we mentioned, is this number is going down significantly. The first RowHammer bit flip, the hammer count required for first RowHammer bit flip is going down, and that doesn't sound good, right? Okay, I've already mentioned these key takeaways. Now, let's take a look at mitigation mechanisms on the other hand. Okay, there are people who propose many mitigation mechanisms, and we want to also evaluate these mitigation mechanisms and how they scale with the results we find. I think this is quite interesting because it's good to also predict the future, let's say. And we evaluate mitigation mechanisms with different metrics, also with a simulator, which you're going to use also in one of the labs, the emulator simulator, which is essentially a DRAM simulator that we have developed over the years, and many people in industry and academia are using it actually, and we're supporting it. But we want to basically look at the bandwidth overhead as well as normalized system performance. I'm not going to show you the bandwidth overhead, but system performance is what matters in the end. But bandwidth overhead correlates with system performance also. If a mechanism is consuming a lot of bandwidth in DRAM, it's going to degrade your system performance because there are applications that are trying to access DRAM, right? Okay, these are the mechanisms we examined. This doesn't include the latest mechanisms that we will maybe talk about, which I believe scale better actually, because the goal of those latest mechanisms were actually to scale better. Let's say they were published after this paper, right? And our goal was to actually have better scalable mechanisms. But you can see paras here, increased refresh rate is here, and some mechanisms that I'm not going to talk about. Some of these are actually modifications to para to make it better. Let's say, I think MR lock is like that. Crowheads is also like that. Twice is a completely different mechanism. That's an access pattern-based mechanism that has complicated tables, let's say. And also we have an ideal refresh-based mitigation mechanism that we call ideal. I'm going to mention that when we come to it. And there's more stuff in the paper. Well, let's take a look at this. This is HC first. As you go from left to right, it reduces, meaning this is the number of hammers required to induce first RowHammer bit flip. And you can think of this as going from left to right as technology scaling, right? And this is the normalized system performance impact of the mitigation mechanism, assuming an HC first. And this is evaluated across a number of applications, workloads, simulation, in simulation. Okay, this is what happens to increase refresh rate, meaning you increase the refresh rate such that you eliminate all the RowHammer bit flips that we see based on experimental data. You need to increase it so much that your system performance, let's say, reduces by 5x, right? So if you go to 20% of your system performance, that means that you lose 5x of your performance, right? Your system slows down by 5x. So it doesn't sound very good, right? And it's not scaling very well, meaning as you need to refresh more and more, you're not going to get rid of the bit flips, basically. Okay. Because you have prohibitively high refresh rates. And we didn't test it because it was ridiculous, right? You don't want to go into 10% of your system performance. Okay. So clearly that was, I mean, as expected also, that was not a good solution, right? But this paper really quantifies it in a nice way, let's say. So para looks like this. It's interesting, right? So when you get to 1,000 hammer counts to induce the bit flips, it starts becoming quite worse, right? 25% performance degradation. And when you get to, let's say, many futuristic hammer counts, like you get a bit flip at 64, after 64 hammers, you can argue that that's probably not a viable solution in DRAM, the viable position in DRAM. But if things keep scaling as they are scaling, maybe there's an end to the DRAM scaling also, right? Because RowHammer will be intolerable, let's say. So there, I think you get 10x performance loss. Your system performance goes down to 10% of its original, let's say. That doesn't sound good also, right? That's why para is not also scalable, right? It works to reasonable hammer counts, but what is reasonable is a question, right? Okay, this is arbitrarily, we said this is the high performance overhead. We don't want more than 10% performance loss, basically. I think 10% is, and people try very hard to gain 10% performance, right? If you lose 10% just because of RowHammer, even that may not be acceptable, right? Maybe even 5% is not acceptable, I don't know. But 80% is certainly not acceptable, I would argue. Okay, pro hits, basically it's here, but it doesn't scale. I'm not going to go through that. You can read the paper for more detail. These other mechanisms are somehow, it's not clear how they will scale. Even though they're okay over here, we don't know if they're scaling very well. Okay, and twice is another mechanism that's actually, we don't know how to scale it, but if you can ideally scale it, it's actually better than para. It's an access counter-based mechanism. Again, I'm not going to go into the details of it because there's a lot of detail in terms of how it works. And some of it is not intuitive also, I will say. Assuming it solves some of the critical design issues it has, it can scale basically. But again, what does can scale mean? It still is not good in terms of performance over here, right? Okay, and the ideal mechanism is actually not that bad. Basically, it issues a refresh command to a row only right before the row can potentially experience a RowHammer bit flip. So you know when the row will experience the RowHammer bit flip, and you have a magic mechanism with no overhead, no tracking overhead. It only issues the necessary refreshes, and then it's not bad until very low RowHammer hammer counts, right? I think this can still be optimized. If you can, for example, so here we assume that all rows are equally vulnerable. That's not true based on the current results. So if you can actually adapt this mechanism, this ideal mechanism, such that you take into account the vulnerability of each row, and it's separate, it's different. So the number of hammers you need to do to induce a bit flip in each row is different, basically. Actually, in our most recent paper, we show that 90% of the rows in DRAM required, I think, hammer counts that are 2x higher than the remaining 10%. So you can actually fix that mechanism. You can actually fix the ideal. The ideal is actually even better. The real ideal is even better than the ideal that we examined, let's say. But of course, that requires some mechanism to make it work, right? Ideal is ideal because it's unachievable today. We don't know how to achieve it. But again, this means that there's potential room for improvement in RowHammer mitigation mechanisms, as you can see. Okay, so 6% performance loss maybe is much better than what we have, at least at this point. I think this point is, I don't know, what is it? 256 hammer count, something like that, perhaps. Okay, so this is where we are basically. This is DDR based on experimental data. If you plot where we are, this is DDR3 old, DDR3 new, DDR4 old, LPDDR14X. Basically, these are 1X is technology node. 1X is higher than 1Y in terms of, so 1X is probably around, I don't know, 16, 17, 1Y is 15, 14. So basically, we're inching our way to the right, as you can see. So as new DRAM chips come, probably we're going to be here. Unless there's some device and circuit level mitigation mechanism that makes them better, right? Of course, we don't know the future. Okay. So basically, the takeaway is that only Paris design scales as it's proposed without having unrealistic assumptions. But even Paris doesn't scale from performance. Its design scales, but performance doesn't scale, as you can see, as we want. An ideal mechanism is significantly better than anything we have today, as you can see. So basically, the takeaway is there's significant opportunity for developing a RowHammer solution with low performance overhead that supports this technology scaling. Does that make sense? Okay. Okay, so I think I've said everything over here. I'm not going to repeat it. There's more detail in the paper, like single cell RowHammer flip probability. That's interesting. Data pattern dependence, error correcting codes. We analyze that also, actually. Again, we find out that they're not good enough, or you need to make them strong enough. And there's additional observations that you can find out. Okay, so let's talk about solutions a little bit more, basically. I think this is going to be important because we really need to solve the problem, right? And I think there are two promising, and the paper also advocates for two promising directions. One is what we've advocated for a long time, DRAM system cooperation. Somehow DRAM and system need to work together. You cannot basically say, okay, DRAM chips are going to handle this. Somehow we need a better memory controller, and maybe memory controller may not be good enough also, right? What if the memory controller, let's say, has too much overhead? Maybe it detects some things and it basically passes on the problem to the operating system, saying, oh, I think somebody's doing a RowHammer attack. Take this application from me and do something else, right? Especially, but I think there is some downside to this also, meaning as the hammer count becomes really small, it becomes difficult to distinguish real applications that are benign versus RowHammer attacks also, right? So I think the future is going to be messy if we really go down to, let's say, 64 hammer counts. I don't know if it makes sense actually to think about 60 hammer counts that lead to bit flips after 64 activations. Maybe that's the end of DRAM scaling. Maybe that's where you declare the technology is not scaling anymore. I'm not going to reduce the size. I'm going to do something different. Yeah, I think yeah, this is something to really think about, because there's no perfect solution at some point, because if your benign applications become looking like RowHammer attacks, what do you do, right? You will lose performance at that point, right? So there are other, of course, we don't know exactly how to do this. We will talk about some solutions that came after this paper. But there's something interesting as well, which is profile guided mechanism, meaning somehow if we can form an accurate profile of RowHammer susceptible cells in DRAM, we can have more targeted solutions. So for example, increase the refresh rate for rows containing RowHammer susceptible cells only. And our recent paper actually makes a step toward this direction, understanding different DRAM cells and different properties. That actually reduces the overhead, some of the mechanisms. And of course, how to do this exactly fast and accurately is actually not so easy. How do you actually come up with a profiling mechanism that's fast and accurate, that discovers all the RowHammer bit flips? If you come up with ideas, you can actually make an impact, let's say. But this is something that all of these are research topics basically currently, and industry is very much interested also actually. Actually, after we published this paper as well as the trespass paper, these have had a lot of impact in industry, saying basically we need to go back to this problem and we need to fix it. And in fact, even though DRAM manufacturers may be quite reluctant, this impact came from many big companies like Microsoft, Google, Amazon, etc. And they basically said, we got to fix this problem because they're the ones who are really using DRAM, right? Other than the poor consumers also, right? Poor consumers don't matter. These other companies matter because those other companies are buying DRAM from these DRAM manufacturers at huge scales, let's say, for their data centers. Yeah, I think poor consumers should also matter, maybe matter more, but well, that's something we cannot easily tackle, at least in this course, because many people try to tackle that, and to have success, you really need to be very persistent. Okay. Okay, I think I've said everything over here, so I'm not going to repeat it. But that was this revisiting RowHammer paper. And I think that brings us to the end of lecture C, 5C. And I'm not going to start 5D because this is going to be an entire, let's say, look back and talking about maybe more, let's say, more fundamentally better solutions to the direction. But we will start this tomorrow, hopefully. And then we will move on to in-memory computation after that. Any questions before we part? Yes, please.
This is a more general question, but when you work on this kind of system on RAMs, are the vendors actually financing your research?
Yeah, that's a good question. Yeah, I think unfortunately, so there was a time when one of the vendors, Samsung in particular, was quite forward-looking, and they actually financed a lot of our research. But I think sometimes it depends on how forward-looking the vendors are, I would say. If they're forward-looking people and they see the value of this sort of research, we got a lot of funding actually at that time. But some people left the company, perhaps because they couldn't also do a lot of change. As a result, that funding stopped. Right now, I think manufacturers have become even more conservative, let's say. Okay. I think some of them may be interested in funding research with the condition that results are not going to be openly published. And that's something not acceptable to me, let's say, as a researcher, right? So that's probably they can fund that way, but I don't want that also. Does that make sense? So funding should be free, and let's say free meaning without those sort of strings attached, right? If you're going to keep it to yourself, then I might work for a company and make even more money than I'm making right now, right? Why am I doing this? But yes, I think it really depends on how forward-looking the people are. And unfortunately, I mean, these are complicated companies also, right? They're huge manufacturing businesses. They've invested a lot into that manufacturing, a particular type of manufacturing. And their business banks on it. But I think sometimes over the course of decades and decades and decades and decades of manufacturing, they get trapped into this dilemma. Some people some business folks said that this is the innovator's dilemma, right? Do you invest into forward-looking research, or do you keep doing what you're doing? And I think some of these companies are really trapped into keep doing what they're doing. And it's kind of like a very myopic viewpoint. If I do anything else, I will lose my competitive edge on this. And some people, I think, correctly name this as innovator's dilemma. Which one do you choose? I think, and they said basically, if you don't choose the innovative research, somebody else may do it, and you can get dislodged from your current position, even though you don't want to get dislodged. So there are a lot of interesting aspects like this also. But I think that's the mindset I see in these big manufacturing businesses. Let's keep on what we're doing. It has worked. It'll work. But maybe someone will manufacture better DRAM, right? Or some better non-volatile memory, as we will discuss later on. Yes.
Like, if these three big DRAM companies keep mitigating RowHammer enough, that a different company might enter that business with a different view on, like less conservative view on mitigating these things.
Yeah.
Or is it just the barrier of entry too high?
Yeah. I think that's a very good question, and that's the innovator has a dilemma, or companies who are settled as a dilemma. Startups also have a dilemma, right? How do you challenge these? Because you don't have the manufacturing base necessarily. I think it's tough. That's a very tough place to be in, right? Because you need to have the manufacturing capability, expertise, and both are really hard to get. Yeah, maybe possible, but so far it has not worked. There are some companies that are smaller, but they don't have the volume also, right? It's not just the fact that you can manufacture, you need to also have the volume, right? So in a sense, I think industry is not in a great position because clearly there's more and more need for DRAM. DRAM prices are actually increasing sometimes, right? People are paying more for more DRAM, let's say. Maybe the bit price is not increasing, but you're getting more DRAM in your systems, for example. So basically, there is a clear need for DRAM, even if it's not perfect, right? So I don't have a good answer to your question other than saying it's tough to dislodge these these big businesses also.
A new entrant would need existing manufacturing capabilities.
Yeah.
So maybe Intel could do it, but for example, Apple couldn't really do it. Just
yeah, maybe not. I mean, of course, the manufacturing capability also needs to be customized to the chip, right? So Intel is very good at logic process, but they got out of the DRAM business in the 1970s, right? So Intel manufactured the first DRAM chip in the world in 1971, I think. But then they got out of the DRAM business. So I don't think their manufacturing capability is or expertise is applicable to DRAM, let's say. Yeah. Yeah, I don't have a good answer. If you have a good answer, let me know. I think this sort of initiative needs to be backed by, I think, a lot of investment, basically. Somebody needs to say, oh, I'm going to invest in this, and I'm not going to get much out of it for a long time. But when I get to the cutting edge, I may actually get a lot out of it, right? Again, so that's very speculative, and that's very, very few people want to take that sort of risk, right?
Yeah, really, the existing manufacturers, like, how long would it take if they somehow started to care at some point in time? I mean, a new entrant would probably take much longer to get to mass market before one of the existing ones suddenly cares and does it better.
Exactly, yeah. There's also that danger, right? And existing ones are also changing their mentality a little bit. They're doing processing in memory, for example. So they're evolving. So it's not like they will not change their mind at any point, right? So it's a very risky place to be in to compete with some of the very established businesses. And I think that's in general true when you have when there are like very small number of players in a market where manufacturing you really have high manufacturing costs, but also very high volumes, right? Yeah, like some of the DRAM manufacturers are actually can manufacture smaller ones, but they cannot get to very high volumes. As a result, their dilemma is they don't get as much attention from people who buy very high volume parts, right? Yes.
Wondering if you knew of any like smaller targeted companies that are focusing on like security first DRAM, because it feels like a lot of these bigger companies don't care because it doesn't make sense for their business model. But are there any like security slanted?
Yeah, I think the smaller companies can potentially do it basically, but of course you need to pay the cost for them. I think clearly, I mean, you don't want to use this DRAM in your self-driving cars, perhaps, or when you go to space, for example. I think increasingly there's more danger with these things. I mean, there are people who try to like harden the chips, etc. But yeah, I think small manufacturers are more viable to that. Like some of them are interested in reducing the latencies even more, for example. So they can experiment more. But of course, somebody needs to pay them also. Okay, I think this is a good discussion. We're over time for sure. I will see you tomorrow. We will continue from, I guess, this point. Take care. Have a good evening. And my battery is almost dead.